Hello there, and welcome to the Sleepy Cosmic Lens. There are moments in astronomy when a familiar corner of the sky suddenly becomes unrecognizable, when a telescope captures something so strange, so out of place, that the universe seems to shift beneath our feet. It happened before with the first exoplanets, with the first black hole images, with the first hints of galaxies older than theory allowed. And now it has happened again when the James Webb Space Telescope turned its gaze toward Alpha Centauri, the closest star system to our own. Astronomers expected clarity. Instead, they found patterns that should not exist, shadows cast by invisible objects, and a planetary system shaped by forces no one had predicted. This is the story of what Webb saw and why it left scientists unsettled. Let us begin when the light from Alpha Centauri shifted. The light that reaches us from Alpha Centauri is usually steady and predictable, a familiar glimmer from the nearest stars beyond our own sun. Generations of astronomers have studied it and found comfort in its reliability. But when the James Webb Space Telescope turned its attention toward Alpha Centauri A, something in that light changed. It was subtle at first, almost buried beneath the overwhelming brilliance of a sun-like star, yet unmistakably present. A faint thermal trace shimmered in the data where nothing had ever been seen before. The moment it appeared, it forced researchers to confront a possibility that had eluded them for decades. This nearby system might not be as quiet or as simple as everyone assumed. What followed inside the observatories and data centers was a controlled chaos. Teams who had spent years modeling how Webb would behave around bright, close stars suddenly found themselves staring at a feature they could neither dismiss nor fully offend. The first two paragraphs close here. From this point onward, the chapter moves directly into the unfolding story without lingering an introduction. The shift in the light was not a single spike or a stray signal. It was a structured pattern in the mid-infrared, far too organized to be background noise, yet too faint to stand out in ordinary circumstances. It emerged only because Webb's coronagraph masked the glare of Alpha Centauri A, creating an artificial night around the star so that faint shapes could materialize from the darkness. In that engineered shadow, something appeared that had no place in existing catalogs or previous surveys. Understanding why this moment struck such a deep nerve requires remembering how many times astronomers searched the Alpha Centauri system and found nothing. For decades, telescopes on Earth and in orbit scanned the region for planetary signatures. The stars were close enough to fill instruments with precision data, yet every attempt to confirm large planets around Alpha Centauri A or Alpha Centauri B ended the same way. The noise of the stars overwhelmed the signals. Stellar activity imitated planets, and orbital motion between the two bright suns created fluctuations that mimicked false positives. Time after time, the system seemed to promise answers only to hide them again behind its overpowering light. The result was a strange contradiction. The closest sun-like stars to our own appeared to be barren, yet no one believed they truly were. That long history of frustration explains why the sudden presence of a possible planet struck with such force. The detection was not a triumphal announcement. It was an interruption of everything astronomers thought they understood. Webb had been built to look billions of years into the past, not 4 light years away. Its optics were engineered to capture galaxies stretched by cosmic expansion, not planets drowned in the glare of a binary system. To even attempt this observation, the operations team had to create a completely new use designed only for Alpha Centauri. They needed to anticipate the interference caused by Alpha Centauri B, and they needed to stabilize the telescope against the rapid apparent motion of the stars across the field of view. The fact that the team managed to extract anything from such a challenging environment was extraordinary. The fact that what they extracted looked like a world was almost unbelievable. The light itself told a complicated story. Webb's mid-infrared instrument picked up a glow consistent with an object much cooler than Alpha Centauri A. This was not a fragment of dust or a distant galaxy. It had the thermal signature of a large body radiating its own warmth. Based on its brightness, researchers estimated a mass similar to Saturn in an orbit that placed it somewhere between 1 and 2 Earth-Sun distances from its parent star. This specific combination was alarming. Gas giants are not expected to form easily in systems dominated by two sun-like stars, whose gravitational pull constantly stretches and compresses the protoplanetary disk. Even if they form, their survival is unlikely. The binary's influence should scatter them inward or outward, or eject them entirely into interstellar space. Yet, the data suggested that one such world was still there. Once the image was processed and the patterns of scattered stellar light were removed, the object became more distinct. This was the moment many on the team later described as unsettling. A planet inside a binary system should not be this stable. It should not be this bright, and most importantly, it should not appear only once. The fact that the detection was captured clearly in the first series of observations, but not in the later ones, deepened the uncertainty. When the team looked again in 2025, the object was gone. It was not fainter. It was not distorted. It was simply missing. This disappearance was more disturbing than the original discovery because it implied motion that did not match simple expectation. A vanishing planet raised the possibility that the system contained orbital interactions complex enough to hide entire worlds for months at a time. As the early results circulated among mission scientists, a single realization emerged. If the detection was real, it would mark the first direct evidence of a planet around a sun-like star in the closest stellar system to Earth. It would become a touchstone for exoplanet science, a laboratory for future missions, and a profound shift in our understanding of how planetary systems form. If the detection was a coincidence or an artifact, it would reveal flaws in the most advanced exoplanet imaging ever attempted. Either possibility carried enormous consequences, and neither could be taken lightly. By the time the chapter of this discovery closed, the situation was no longer merely an astronomical puzzle. It had become a warning that the region beyond our sun is far more complex than imagined. The nearest stellar neighbor is not a quiet, predictable place. It is a system filled with shadows, shifting light, and structures that appear and vanish without explanation. The glow Webb captured was only the first sign that something unexpected waits within those stars. And now, scientists had no choice but to follow the trail that faint light had. The stars next door that refused to behave normally long before the James Webb Space Telescope revealed anything unusual within Alpha Centauri. Astronomers already understood that this system was unlike any other in the solar neighborhood. At first glance, Alpha Centauri A and Alpha Centauri B appear almost comforting, two warm and familiar suns shining side by side in the southern sky. They seem steady and predictable, a binary pair locked in an elegant celestial rhythm. Yet, beneath that serene appearance lies a far more complicated truth. These two stars are gravitational partners in a relationship so intricate that it stretched the limits of early astronomical instruments and continues to challenge even the most advanced telescopes today. Their behavior is shaped not by simplicity, but by subtle interactions that transform the region around them into one of the most dynamic environments known to exoplanet science. The first and most striking feature of Alpha Centauri A and Alpha Centauri B is their motion. Alone, each star would drift quietly across the sky. Together, bound by gravity, they swing around a shared center of mass in long elliptical arcs that take 80 years to complete. During part of this cycle, they drift far apart, creating a wide and relatively calm separation. But then their paths bend inward again, pulling them into a tighter approach where their combined brilliance overwhelms the darkness around them. This repeated narrowing and widening of the orbital gap does not merely change the star's appearance, it alters everything about the space between them. Dust flows differently, light scatters differently, and the gravitational field twists and stretches in ways that make stable planetary orbits difficult to predict. For astronomers who attempt to observe this system, the result is a constant battle against the unexpected. The two stars grow brighter and dimmer relative to each other as their positions change. Their combined glare saturates detectors, and their overlapping halos produce interference that hides faint details. Even the most sensitive instruments struggle to unravel which features belong to Alpha Centauri A, which belong to Alpha Centauri B, and which belong to neither. When telescopes track objects farther away, such as Proxima Centauri or distant star clusters, their paths across the sky appear almost still. But Alpha Centauri A and B move quickly, covering noticeable distances over months instead of decades. This rapid motion means that any observing plan created for them becomes outdated almost immediately. The complexity does not end with brightness or motion. The stars themselves behave differently from what astronomers expect of sun-like objects. Alpha Centauri, it resembles our sun in mass, temperature, and luminosity, yet subtle differences in its surface activity create noise patterns that mimic planetary signals. Alpha Centauri B, slightly smaller and cooler, sends out bursts of high-energy radiation strong enough to distort readings around Alpha Centauri A. These fluctuations change on timescales that disrupt long-term measurement. A shift that might be identified as a planet in another system becomes uncertain in this one because of how the stars themselves behave. Instruments built to detect tiny periodic changes often find themselves misled by the star's natural rhythm. This constant variability created a challenge so severe that some astronomers believed searching for planets around Alpha Centauri A and Alpha Centauri B was futile. Radial velocity surveys, which detect subtle gravitational pulls from orbiting planets, produce signals that change too quickly and too irregularly to be reliable. Transit searches, which rely on a planet crossing in front of its star, failed because the binary geometry made the odds of alignment extremely small. Even direct imaging attempts were complicated by the brightness contrast. The stars were simply too dominant. For decades, each method broke against the same wall. The system was too bright, too close, too active, and too intertwined for easy analysis. These difficulties created their own strange consequence. As telescopes became better at discovering planets around distant stars, the closest sun-like system remained empty. It was a scientific embarrassment. Researchers could detect rocky worlds around stars 100 light-years away, yet they could not confirm a single planet around the nearest solar twin. The more instruments improved, the more conspicuous this absence became. It suggested either an unlikely coincidence or an extraordinary truth. Perhaps Alpha Centauri A and B formed without large planets, or perhaps the planets were there, but hidden behind layers of noise so thick that even the best tools could not uncover them. When the James Webb Space Telescope joined the search, the scientific community did not expect a breakthrough. Webb was designed for deep cosmic observations, not for navigating the difficult terrain around bright binary stars. Yet, its mid-infrared capabilities offered something no previous telescope possessed. It could see thermal signatures where visible and ultraviolet instruments could not. It could detect the faint warmth of planetary atmospheres or cloud layers. Most importantly, its coronagraph could block the overwhelming light from Alpha Centauri A with a precision unmatched by any previous mission. This meant that for the first time, astronomers could create an artificial eclipse around the star, revealing regions that had been inaccessible for generations. Even with these advantages, observing the system was far from straightforward. Alpha Centauri B remained close enough to scatter its own light into the field, producing arcs and ripples that distorted the data. Webb's detectors had to capture frames faster than usual to keep up with the star's motion. The orientation of the telescope had to be adjusted repeatedly during exposures to counter subtle shifts in angle. Every second of observation required compensating for effects that did not exist around more distant and stable stars. The team had to subtract patterns of light created not only by the stars, but by the telescope itself. They had to compare the images to reference observations, adjusting for each reflection and diffraction spike before any potential planetary signal could emerge. Yet, through all of this, the system's strangeness remained its defining feature. Alpha Centauri A and Alpha Centauri B are close enough to exert profound influence on each other, but far enough apart to allow pockets of stability. They are bright enough to blind instruments, but spaced in a way that leaves narrow corridors where something faint can slip through. They move quickly enough to complicate observations, but predictably enough that their paths can be modeled with precision. It is a system of contradictions, and those contradictions are precisely what make it so dangerous to interpret and so irresistible to pursue. The world that appeared and vanished in Webb's first survey may exist in one of those narrow corridors. It may move through regions where the binary's glare hides it, then reappear when conditions align. The only certainty is that the stars next door do not behave in any way that makes this search easy. And in their unpredictable behavior lies the next step toward understanding what Webb saw when the light shifted for the first time. The hidden star at the edge of the system. While Alpha Centauri A and Alpha Centauri B draw most of the attention with their brilliant, intertwined motion, the third star of the system lingers in the shadows far beyond their reach. Proxima Centauri is so faint that it cannot be seen with the naked eye, yet it holds a place of extraordinary importance in the story of our nearest stellar neighborhood. Its small size, its dim red glow, and its violent temperament create an environment unlike any that surrounds the two brighter suns. And despite its humble appearance, Proxima Centauri possesses a collection of worlds that may be among the most intriguing in the entire galaxy. To understand what James Webb discovered near Alpha Centauri A, we must first understand the complex presence of this distant sibling star that silently shapes the entire system. Proxima Centauri is a red dwarf, the smallest and coolest class of main sequence stars. Its mass is barely more than a tenth of our sun's, and its brightness is so low that even powerful backyard telescopes struggle to pick it out. Yet it is closer to us than either Alpha Centauri A or Alpha Centauri B, hovering at a distance of just over 4 light-years. It drifts around the central pair, not in decades, but in hundreds of thousands of years. Its orbit is so vast that humanity has existed for only a fraction of a single revolution. If the Alpha Centauri system is imagined as a great cosmic stage, Proxima Centauri stands at the far edge, distant yet essential, a quiet actor whose presence changes everything. What makes Proxima Centauri particularly important is the family of planets that circle it. The most famous is Proxima b, a rocky world discovered in 2016 that instantly captured the imagination of scientists and the public. Its mass is only slightly greater than Earth's, and it resides in the star's habitable zone. Theoretically, liquid water could exist on its surface under the right atmospheric conditions. This alone made Proxima b a landmark discovery. No other potentially habitable planet lies anywhere near as close. Yet, the hope stirred by this world is complicated by the harsh reality of its orbit. Proxima b circles its star at a distance so small that it completes a full year in just 11. This places it under the constant threat of intense radiation from the star's frequent and unpredictable flares. The nature of red dwarfs makes them both promising and hazardous hosts for planets. Their long lifespans provide billions of years of steady energy, which is ideal for life to develop, but their magnetic activity produces explosive bursts of radiation capable of stripping atmospheres from unprotected worlds. Proxima Centauri is especially notorious for its violent outbursts. Some flares release more energy than the most powerful flares ever recorded from our sun, and they occur with startling regularity. These eruptions bathe the region in high-energy particles, ultraviolet light, and currents of charged plasma that can erode atmospheres and sterilize surfaces. Any world orbiting so close must carry a magnetic field strong enough to shield itself, or else life would struggle to survive. This creates a landscape of extremes for Proxima b. Because it orbits so near the star, it is likely locked in a state where one side always faces Proxima Centauri, while the other side remains in permanent night. The day side endures unending radiation and temperatures capable of boiling water. The night side sits in a deep freeze so cold that any atmosphere might collapse into frost. Yet, between these two hostile regions lies a thin ring of possible habitability known as the Terminator Zone. In this perpetual twilight, temperatures may stabilize long enough for liquid water to flow. Wind circulating between the light and dark hemispheres could distribute heat, clouds could form, and oceans might appear. If life exists on Proxima b, it would evolve under dim red light and constant tension between warmth and cold. Proxima Centauri also hosts two additional worlds that add complexity to its system. Proxima c is a larger, colder planet that orbits far beyond the habitable zone. It may be a mini Neptune covered in ice and wrapped in a deep atmosphere of volatile gases. Its surface would be frozen to temperatures far below anything seen on Earth. Proxima d, on the other hand, is a tiny rocky world that orbits even closer than Proxima, with a year lasting only a few days and temperatures hot enough to destroy most known materials. Proxima d represents the innermost edge of what a planet around a red dwarf can. Together, these three worlds form a chain of environments ranging from scorching to frozen, a natural laboratory for understanding how planets adapt to the intensity of red dwarf stars. Despite the challenges posed by Proxima Centauri, the system remains one of the most important destinations in astronomy. It is the closest home of known exoplanets. It represents the first stepping stone for interstellar exploration, and it sits close enough for future probes or advanced telescopes to study in unprecedented detail. Projects such as Breakthrough Starshot were designed with Proxima Centauri as their first destination, imagining fleets of tiny spacecraft riding beams of light at a fraction of the speed of light. If such a mission succeeds, Proxima b could become the first planet outside our solar system to be photographed directly. This relationship between Proxima Centauri and the main binary pair plays an unexpected role in the larger mystery of Alpha Centauri. Though Proxima's orbit is immense, the gravitational influence it exerts over hundreds of thousands of years can subtly reshape the orbits of any planets around Alpha Centauri A and Alpha Centauri b. Dust flows between the stars, and long arcs of force interact through time. The three-star system behaves not as isolated components, but as a single interconnected structure. Proxima Centauri may be distant, but its presence changes the gravitational landscape enough to affect planetary stability near the central pair. This connection becomes important when examining the disappearance of the object seen by the James Webb Space Telescope. If a gas giant truly orbits Alpha Centauri A, then over millions of years, the gravitational pushes from both Alpha Centauri b and Proxima Centauri could have shaped its orbit into something eccentric or unstable. It may drift through regions where it is visible in one season and hidden in another. It may cross areas where the coronagraph cannot reveal it. It may be part of a system whose architecture is influenced by forces acting from far beyond the immediate binary. The planet Webb, glimpsed for a moment, may be moving along a path carved by all three stars over ages longer than human history. Proxima Centauri is a faint point of light, but its existence transforms everything we know about the nearest star system. It serves as a reminder that even the quietest member of a system can hold enormous power. It shapes the potential for habitability, the evolution of planets, and the architecture of space itself. And as astronomers continue to search for answers about the world that appeared near Alpha Centauri A, they must account for the influence of this distant hidden star whose quiet glow masks a storm of forces at work. The search that spanned generations. Long before the James Webb Space Telescope recorded its first unusual signal from Alpha Centauri A, astronomers had already spent lifetimes trying to uncover the truth hidden within this system. The search began not with advanced detectors or intricate orbit models, but with simple telescopes that could barely resolve the stars themselves. Even in those early days, the brightness and closeness of Alpha Centauri A and Alpha Centauri b captivated scientists. They represented the nearest example of a system similar to our own, a natural laboratory just beyond the reach of the naked eye. If Earth-like planets existed anywhere outside our solar system, researchers believed this would be the place to find them. That belief set into motion a pursuit that would span decades and ultimately expose how difficult the universe can be when it chooses to guard its secret. In the 20th century, astronomers relied on radial velocity measurements to detect planets by observing tiny shifts in a star's motion. The technique worked well for stars farther away, but Alpha Centauri A and Alpha Centauri b created a unique obstacle because they orbit each other. Their combined gravitational pull produced shifts in their motion that were far greater than anything a planet could generate. The signal from a Jupiter-sized world is small compared to the binary motion, and the signal from an Earth-sized world is nearly impossible to detect. Even when instruments grew more sensitive, the overlapping velocities of the two stars created patterns that looked promising at first, but dissolved under deeper analysis. Some early detections were celebrated briefly, only to be withdrawn when additional data revealed they were artifacts of the binary interaction. As technology improved, researchers turned to transit methods that searched for the slight dimming caused by a planet crossing in front of its star. For distant stars, the geometry of planetary orbits often aligns favorably enough for this method to detect worlds reliably, but the geometry around Alpha Centauri was nothing like those distant systems. The tilting and shifting of the binary orbit drastically reduced the chance of a planet aligning perfectly with our line of sight. Even large worlds would pass unnoticed, never crossing the star's face from our perspective. As astronomers studied the orbits more closely, they concluded that the probability of detecting a transit from this system was small, bordering on negligible. The method that had revealed thousands of planets across the galaxy was almost useless here. Another approach involved searching for the slight wobbling of starlight caused by planets tugging on their host stars. Observatories on Earth devoted countless hours to analyzing these subtle brightness variations. Yet Alpha Centauri A and Alpha Centauri B once again refused to cooperate. Their combined brightness overwhelmed detectors, causing interference patterns that drowned out faint planetary signatures. Even when observatories attempted to isolate each star separately, the proximity of the other star distorted the measurement. Researchers began to suspect that if Alpha Centauri A or Alpha Centauri B possessed planets, those worlds would remain hidden behind a layer of noise too dense for any instrument to penetrate. As years passed without confirmation of planets, a quiet debate grew within the scientific community. Some believed the system truly lacked large planets, and that the early protoplanetary disk had been too unstable for significant worlds to form. Others argued that planets must exist but were hidden so deeply within the binary's complexities that they would only be revealed by a future generation of telescopes. The conflict heightened when discoveries around other stars accelerated, while surveys uncovered worlds around dim red dwarfs and massive blue stars. Alpha Centauri remained stubbornly empty. This absence stood in stark contrast to the growing understanding that planets are common throughout the galaxy. Small hints appeared now and then. Certain observations from large ground-based telescopes suggested that a world might orbit Alpha Centauri B, though the evidence never reached the strength needed for confirmation. A different set of measurements pointed toward the possibility of dust structures around Alpha Centauri A, perhaps caused by the presence of unseen planets. Yet each clue faded under scrutiny, leaving researchers with fragments rather than firm conclusions. The system became a puzzle with missing pieces and no clear way to assemble them. Despite these setbacks, interest in Alpha Centauri never waned. The system was simply too important to ignore. Its distance from Earth made it the ideal target for future interstellar missions. If humanity ever built ships capable of crossing the void between stars, their destination would almost certainly be Alpha Centauri. This possibility kept the system firmly in the spotlight, even as decade after decade passed without a breakthrough. The absence of results did not discourage researchers. Instead, it fueled a determination to develop new technologies capable of piercing the system's defenses. The arrival of the James Webb Space Telescope marked a turning point in this long pursuit. Webb was not designed specifically for nearby stars, yet its capabilities offered something entirely new. It could see in wavelength, where the glare of bright suns becomes easier to suppress. It carried coronagraphs capable of masking starlight with extraordinary precision. Most importantly, it possessed the sensitivity required to detect faint thermal signatures from objects far smaller and cooler than the stars themselves. For astronomers who had spent their careers confronting the limits of earlier tools, Webb represented the first instrument powerful enough to shift the balance in their favor. When Webb finally observed Alpha Centauri A, the moment carried the weight of decades of unresolved searching. Entire careers had been built around the hope of finding something in this system. Many of the researchers analyzing the data had grown up hearing about the failed attempts of previous generations. Now they were watching patterns appear in the mid-infrared that none of those earlier instruments could have detected. The faint glow revealed by Webb was not simply a data point. It was the culmination of years of longing, frustration, and persistence. The search that had stretched across half a century was no longer defined by absence. Something had appeared, something that did not fit any prior model, something that vanished in later observations but left behind enough of a trace to force a reassessment of everything that came before. For the first time in the history of the Alpha Centauri system, astronomers could no longer say there were no planets to be found. They had seen something, and that one moment was enough to unravel the certainty that had built up over generations. When Webb's mask revealed a flicker of something impossible, when the James Webb Space Telescope turned its gaze toward Alpha Centauri in the late months of 2024, the observation seemed almost routine. Webb had already spent years delivering images from the deepest reaches of the universe, revealing structures older than galaxies and starlight stretched across cosmic time. Observing a nearby star, even one as bright and complicated as Alpha Centauri A, should not have carried the same sense of mystery. Yet, from the very first moment the coronagraph was engaged, and the light of the star began to dim behind its artificial shadow, the research team sensed that this was no ordinary target. The faint glow they hoped to detect would be unlike anything Webb had attempted before. It required stunning precision, careful planning, and a willingness to peer into the most challenging region of the sky for exoplanet detection. The coronagraph aboard Webb is a technological marvel. It works by blocking the blinding glare of a star so that the space around it becomes visible. Without this mask, the heat and brilliance of Alpha Centauri A would overwhelm the detectors, drowning out every faint signal that might lie nearby. The instrument is effectively an engineered eclipse, a way to mimic the deep darkness created when the moon obscures the sun. Yet, unlike a natural eclipse, this one must remain perfectly aligned. Every vibration, every shift in temperature, and every minor distortion in the telescope's mirrors has the potential to break the illusion and allow starlight to spill back into the frame. This is why the observation sequence required so much preparation. The team at the Space Telescope Science Institute designed a special routine only for Alpha Centauri A, accounting for the interference from Alpha Centauri B and the unique challenges posed by the binary motion. As the coronagraph darkened the star, the initial images were filled with arcs of scattered light. These are common artifacts in coronographic imaging. The mask blocks the brightest core of the star's glow, but the outer regions still bend around the edges of the mask, creating ripples of illumination that spiral outward. Additional diffraction patterns are produced by the support structures that hold Webb's mirrors and by microscopic irregularities in the telescope's optical path. In an ideal environment, these patterns are predictable enough to remove through careful processing. In the Alpha Centauri system, however, the presence of the companion star added complexity. Alpha Centauri B cast its own reflections across Webb's field of view, producing streaks and rings that drifted slowly over time. Untangling these layers of contamination required reference images, elaborate mathematical modeling, in comparison to earlier calibrations stored deep within Webb's operational archive. For hours, the team watched as the data streamed down from deep space. The images were messy at first, swirling with enough light to hide any subtle signal, but with each round of processing, more clarity emerged. Known patterns of interference were removed, leaving behind a smoother backdrop. Thermal fluctuations were filtered out, and residual glare from Alpha Centauri B was subtracted using frame differencing techniques. The process was slow and methodical, and for much of it, the images looked disappointingly empty. Yet, near the edge of one of the masked regions, something faint began to appear. It was not a sharp point like a distant star, nor a stretched smear like a galaxy. Instead, it was a tiny rounded glow that seemed to hold its shape across several consecutive frames. At first, the team suspected a noise artifact. Instruments as sensitive as Webb occasionally produce false signals caused by cosmic rays or temporary detector variations. But this glow did not behave like noise. It was present in each corrected frame, shifting slightly in position as Webb adjusted its pointing, but maintaining a consistent brightness pattern. The effect was subtle but unmistakable. Once seen, it could not be unseen. The team began to refine the image further, removing even the faintest remnants of glare. With every layer peeled away, the object it sat at a distance from Alpha Centauri A that matched the region where a planet could theoretically reside without being torn apart by the pull of Alpha Centauri B. Nothing about its appearance made sense at first. The glow was too bright to be a distant galaxy and far too symmetrical to be a dust clump. Its thermal signature, captured in the mid-infrared, matched the expected emission from a gas giant several times smaller than Jupiter. The brightness indicated a temperature similar to that of the gas giants in our solar system, and the location fit orbital models that had been considered possible but remained unproven. As the realization spread through the team, the atmosphere inside the control rooms shifted. The excitement was tempered by caution, but it was excitement nonetheless. For decades, the system had yielded no firm evidence of planets. Now a faint but convincing signal hovered on their screens. The decision to treat the object as a potential planet candidate did not come lightly. The team compared the new detection to older ground-based observations, including the 2019 event recorded by a major observatory in the southern hemisphere. That earlier observation had shown a similar glimmer at nearly the same position, though not strong enough to confirm. When the new signal from Webb aligned with that older trace, the coincidence became difficult to ignore. The possibility grew stronger that both observatories had seen the same object at different points in its orbit. As the night progressed, the team ran simulations to estimate the mass and orbit of the object based on its brightness. The results pointed to a world approximately the mass of Saturn, moving through a region located between 1 and 2 times the distance between Earth and the Sun. That distance was both surprising and unsettling. A gas giant in such a place should not exist in a system dominated by 2 bright stars whose gravitational fields constantly tug at each other. Yet, the data suggested that it was not only present, but remarkably stable. By the time the analysis concluded, the researchers understood the significance of what they had seen. They had captured direct evidence of a possible planet around Alpha Centauri A, something no telescope had ever accomplished. They had pierced the blinding light of the nearest sun-like star and found a faint object where theory predicted only chaos. The glow was small, fragile, and easily lost, but for that moment it existed, and that single flicker was enough to change the trajectory of the entire investigation, opening a doorway into a mystery just beginning to unfold. How a planet can appear and then vanish. When the James Webb Space Telescope returned its second set of observations of Alpha Centauri A in the early months of 2025, the research team expected to see the faint object again. After all the care invested in the first detection, the logical next step was confirmation. A single appearance could always be questioned, but a repeated one would become evidence strong enough to transform a fragile signal into a verified world. The team had prepared for that moment with quiet confidence. They refined their processing sequences, recalibrated their coronagraphic masks, and strengthened their models so that the new images could be compared directly to the earlier ones. But when the first frames appeared, the object that had generated so much excitement was nowhere to be found. The darkness near Alpha Centauri was empty. The area where a planet should have been was blank. The initial reaction was not alarm, but skepticism. The team assumed that the object must have drifted behind a region of scattered light, or slipped into an area where the coronagraph could not detect it. They knew that coronagraphic observations come with blind spots, zones where imperfect masking allows small bursts of starlight to overwhelm fainter signals. Because Alpha Centauri is so bright and Alpha Centauri b so close, those blind spots can shift unpredictably as the stars move across the field of view. The first pass through the data showed the same interference patterns as before, ripples and arcs from the star that needed to be removed. It was entirely possible that the planet's glow was simply obscured by the noise. Yet, as the data were processed further and distortions were peeled away, one by one, the emptiness remained. The object did not reappear. The region around Alpha Centauri A had been swept clean with remarkable precision, and still nothing emerged. When the team repeated the analysis using different algorithms, the results stayed the same. The object had vanished. A third round of observations in April brought the same unsettling silence. For months, the star showed no trace of the faint glimmer captured the previous year. What had looked like the first direct image of a world near a sun-like star in our neighboring system was gone without leaving even a residual outline. This disappearance was not merely frustrating, it was deeply troubling because it suggested that the object might be moving in ways that defied earlier expectations. Planets do not blink in and out of existence. They follow predictable paths. They move gradually across the sky. They do not appear brightly at one moment and vanish the next. If the glow seen in 2024 had been a temporary flare or a dust clump drifting through view, its signature would have faded gradually. If it had been a background galaxy passing behind an area of heavy diffraction, it would likely have shown some distortion or movement. Instead, the object behaved as if it had slipped behind an invisible curtain. When the team explored the possibility that the object had been a noise artifact, they found that explanation unsatisfactory. Noise does not produce a consistent thermal signature across multiple frames. Noise does not remain stable in location and shape while the telescope adjusts its pointing. Noise does not match the brightness profile of a gas giant. The signal from the previous year had been too clean and too structured. It was not something that appeared across a single frame and disappeared in the next. It persisted long enough to be extracted through layers of heavy processing. It behaved like a real object, not a computational illusion. As the mystery deepened, the team turned to orbital modeling. They needed to determine whether the planet could have moved into a region where the coronagraph was effectively blind. These models considered every known constraint. They included the relative positions of Alpha Centauri A and Alpha Centauri B, the brightness of the object, the expected orbital distances where a gas giant could survive, and the stability zones within the chaotic gravitational environment of the binary system. Researchers simulated millions of possible orbits, tracking how a Saturn-mass planet might behave under the combined pull of the two stars. The results of these simulations offered a surprising explanation. In nearly half of the stable orbital paths, the planet would have moved closer to Alpha Centauri A during the months between the observations. Such motion would place it inside the innermost region, where Webb's coronagraph could not detect it. The planet would not become dimmer, it would remain just as bright. But from Webb's perspective, the glare of Alpha Centauri A would overwhelm it completely. In effect, the planet would be hidden behind the star's radiance like a firefly lost in broad daylight. This possibility meant that the disappearance was not a sign that the object was illusory. It was exactly what would happen if the planet had followed one of the many viable orbital trajectories. However, this explanation raised an unsettling implication. A planet capable of slipping in and out of detectability over such short timescales would need to follow an orbit that was not perfectly circular. It would likely move through an elliptical path, drawing closer to Alpha Centauri A at certain times and drifting farther away at others. In a system governed by a central star alone, such an orbit could be but in a system dominated by two bright suns, the gravitational influence becomes far more complex. The tug from Alpha Centauri B could stretch the planet's orbit, altering its shape as resonances could form. The orbit could precess, and it might even oscillate between stable states, shifting in subtle ways that cause the planet to vanish during specific observing windows. This behavior was not what astronomers hoped for, but it was exactly the kind of behavior that would make the system far more dangerous than expected. A giant planet moving along a path shaped by two stars could easily disrupt smaller worlds. It could sweep through regions where rocky planets might otherwise survive. It could destabilize dust rings and gravitational niches. Its presence alone might explain why Alpha Centauri E and Alpha Centauri B had seemed devoid of smaller planets for so long. A giant planet with an eccentric orbit could have cleared them out long ago. The disappearance also highlighted a deeper truth. The Alpha Centauri system may not be a quiet and orderly arrangement of stars and planets. It may instead be a dynamic environment where worlds shift unpredictably, influenced by gravitational tides that operate over years, decades, and millennia. The object seen by Webb had not vanished. It had moved beyond our view, slipping into a corridor of brightness where even the most advanced instrument humanity has ever built could no longer detect it, and that behavior suggested that the system's architecture is far more intricate than anyone had imagined. The pattern in the darkness that should not exist. The months following the disappearance of the faint object near Alpha Centauri A were filled with a kind of restless analysis that only emerges when a discovery contradicts the expectations of an entire field. Researchers across observatories studied the data with increasing intensity, searching for clues hidden not in what was seen, but in what was absent. If the object Webb captured in 2024 was truly a planet, then its disappearance should have followed a pattern. Something in the orbital mechanics, brightness behavior, or thermal signature should reveal where it had gone. But the Alpha Centauri system has a way of turning familiar expectations into complex puzzles, and the unfolding analysis revealed a pattern that was both subtle and deeply unsettling. The first anomaly appeared when researchers began comparing the Webb data with older infrared surveys of the region. Even though previous instruments lacked the sensitivity to detect a small gas giant directly, they still recorded faint background fluctuations. These fluctuations appeared insignificant at the time, but they gained new meaning when placed alongside the Webb coordinates. A handful of the old survey points contained slight thermal enhancements not aligned with the positions of Alpha Centauri A or Alpha Centauri. When plotted together, these points traced a loose arc that sat far outside the binary's main gravitational interaction zone. At first, the arc looked like an observational artifact, the kind of accidental curvature that emerges when faint noise aligns by chance. But when the team overlaid the coordinates of the object Webb had detected, the two patterns intersected almost perfectly. This was unexpected. It implied that the faint glow Webb recorded might not be the object's first appearance, but rather the brightest point in a long, subtle trail spanning years of observation. If true, the object was not behaving like a typical planet with a simple orbit. Instead, its thermal signature appeared intermittently in different surveys, always faint, always near the edge of detection, and always following a path that suggested long-term movement through space. The arc could represent a fragmentary record of the planet's journey, captured unintentionally by instruments never built to see it. The idea was compelling, but raised a difficult question. Why would the planet's brightness vary? Planets do not naturally flicker unless something unusual shapes their atmospheres or their illumination. To refine the pattern, the team used a model that incorporated the gravitational influence of both Alpha Centauri A and Alpha Centauri B, as well as perturbations from Proxima Centauri over long time scales. When they ran simulations that allowed the planet to follow rare but stable resonant paths, a strange possibility emerged. The object could be trapped in a type of orbital resonance that caused it to move in and out of regions where stellar light intensifies and weakens. In practical terms, this meant the planet could grow warmer when passing through certain parts of its orbit, and cooler when drifting into others. The warming and cooling would produce faint changes in the infrared brightness, making the planet easier to detect at one time and invisible at another. While such resonances are rare, they are not unheard of in multi-star systems. However, this particular pattern suggested a resonance far more extreme than typical planetary interactions. The analysis became even more unsettling when the team introduced another factor. If the planet possessed one or more large moons, their combined gravitational influence could amplify the resonance effect. The moons would pull on the planet's atmosphere, altering circulation patterns and potentially driving large-scale temperature shifts over months or years. This would create a flickering thermal signature, one that could appear in archival data at irregular intervals. And because such moons would have their own thermal contributions, they could imprint faint variations on the curve detected by older surveys. Suddenly, the arc of faint points no longer looked coincidental. It resembled a fragmented echo of a more complex system. The presence of moons orbiting a gas giant near a binary star might sound improbable, but the parameters of Alpha Centauri have always resisted normal expectations. If the system once contained a more massive protoplanetary disk, the formation of large moons could have been possible before the binary's gravitational interactions reshaped the region. These moons could remain stable if they orbit the planet tightly enough. Their presence would help explain why some thermal points in the older surveys were slightly offset from where the planet alone should be. The pattern, once dismissed as noise, now hinted at a system of objects moving together in a dynamic gravitational dance. Yet another interpretation emerged as researchers dug deeper. The arc did not perfectly match the shape expected from a stable multi-moon configuration. Instead, it bent more dramatically at certain points, almost as if the planet's orbit underwent periodic distortions. This led to a more alarming possibility. The planet might be experiencing gravitational forcing strong enough stretch or compress its orbit over short timescales. These deformations would not be random. They could be caused by passing near a region where the gravitational pull from Alpha Centauri A and Alpha Centauri B overlaps in a complex way. Such regions, known as transitional zones, can cause planets to speed up or slow down slightly as they pass through. The effect is subtle but powerful enough to shift the timing of when a planet might appear in coronagraphic observations. If this interpretation is correct, then the faint signals in the older surveys represent not just glimpses of the same world, but evidence of an orbit undergoing periodic stress. This type of behavior has been predicted in advanced simulations of multi-star systems, but has rarely been observed directly. A planet experiencing such gravitational forcing could undergo tidal heating in its interior, generating additional infrared emission. This would make it bright at certain points and dim at others. The thermal arc across the archival data might therefore be a record of the planet's internal heat, rising and falling as its orbit was stretched and squeezed by the combined pull of the nearby stars. This idea carries profound implications. If the planet experiences tidal heating on a significant scale, then its interior could be far more active than those of the gas giants in our own system. It could host storms larger than any seen on Jupiter. It could eject heat through deep atmospheric channels. Its cloud structures could flicker like moving shadows. These features would all contribute to irregular infrared signatures captured unintentionally in older surveys. The more researchers examined the pattern, the more the disappearance of the planet in Webb's second round of data resembled not a contradiction, but a confirmation. It behaved exactly as an object undergoing tidal forcing and thermal cycling would behave. When it drifted into cooler regions or behind a bright zone of stellar interference, it vanished from Webb's view. What emerged from this analysis was not a neat explanation, but a realization that the system contained an object whose behavior aligned with none of the simple models used to describe exoplanets. It followed a path visible only in fragments, detectable only in certain wavelengths, and shaped by forces far more complex than those governing planets in our own solar system. The pattern in the darkness would not have existed, yet it did, and its presence suggested that the Alpha Centauri system was not merely hiding a planet, but revealing the first signs of a world that behaves in ways no one expected, the orbit that no model wanted to accept. As astronomers dug deeper into the growing puzzle of the Alpha Centauri candidate planet, they reached a point where traditional orbital mechanics no longer offered satisfying answers. The object's faint thermal trail, its brief appearance in the James Webb data, and the subtle flickering found in older infrared surveys all pointed toward motion that was neither circular nor stable in any ordinary sense. The research teams across Europe, the United States, and Australia began refining their simulations, feeding in updated mass estimates, gravitational models, and proximity effects from the nearby binary star. The result was a pattern of orbital solutions that did not resemble the clean, predictable paths that govern most planetary systems. What emerged instead was an orbit so unusual that the first reaction from many astrophysicists was disbelief. The initial expectation had been simple: a gas giant around Alpha Centauri. A should follow one of a handful of stable orbits constrained by the gravitational pull of Alpha Centauri b. Those stable zones had been mapped long ago, stretching outward like narrow bands where a planet could survive without being pulled apart or thrown into deep space. Yet, when the simulations accounted for the faint signals seen across multiple surveys, the planet appeared to drift between the outer edges of two of those stability bands. This suggested that it was traveling along a track that dipped into a region where gravitational forces from the two stars nearly cancel one another out. Such regions are notoriously unstable. A planet wandering through them should, in theory, either crash inward toward the host star or be ejected outward over millions of years. Yet this object had not done either. It persisted, it moved, it reappeared in data years apart. This led the teams to consider an orbital configuration far more complex. In multi-star systems, rare orbits known as liberating paths can exist. These are orbits where a planet does not travel in a simple ellipse, but oscillates around a point that is itself in motion. The object essentially surfs on the shifting gravitational landscape, sliding back and forth like a pendulum while also circling the star. Libration can keep a planet stable in a region that appears ancient at first glance, but libration requires precise timing and the right mass ratios. A slight disruption from a passing comet, a nearby dust ring, or a pulsation from the star could destabilize it. Because of this, liberating planets are considered highly improbable. Yet when the teams fed the Alpha Centauri data into extended simulations, the most consistent solution pointed to a type of drifting libration. The idea was strange enough, but further analysis made it even stranger. The simulations indicated that the planet's path may not be determined solely by the gravitational influence of Alpha Centauri A and Alpha Centauri b. There may be additional mass near the outer edges of the system that contributes to its motion. This mass would not need to be a planet. It could be a belt of dust, a region of small icy bodies, or even a swarm of objects similar to the Kuiper belt in our own solar system. Such a structure would tug on the planet just enough to create a long-period wobble in its orbit. This wobble could push the planet closer to the coronagraphic blind zone during certain years, making it invisible to Webb even though it remained present. What made the situation even more intriguing was the timing. When the team compared the estimated wobble period with the archival signals, they discovered a loose correlation. The faint thermal points that appeared in older data lined up roughly with the predicted moments when the planet would pass through the warmer part of its liberating cycle. These moments corresponded to positions where the combined starlight from Alpha Centauri A and Alpha Centauri b reflects more efficiently off the upper layers of a gas giant's atmosphere. During those periods, the planet would brighten enough to appear faintly in infrared. When it drifted away from that region, it would cool slightly and fall below detection thresholds. The correlation was not perfect, but it was close enough that the researchers could no longer dismiss it. This sent astronomers back to models of planetary formation. A liberating orbit of this complexity would not form easily. It would require the planet to have been influenced by multiple gravitational events over billions of years. Perhaps it had formed farther out and gradually migrated inward. Perhaps it had once shared its region with another massive object that had since been ejected or absorbed by one of the stars. Perhaps Proxima Centauri's distant pull had shaped its motion over hundreds of thousands of years. In these scenarios, the orbit we observe today would be the final state of a long evolutionary battle. What remains is not a clean circular orbit, but a gravitational compromise, a path carved by forces acting from many directions. The more the simulations evolved, the more astronomers realized how fragile the planet's orbit truly was. A system with two bright stars creates constantly changing gravitational tides. These tides can subtly reshape orbits over time, stretching them into elongated shapes or twisting them into misaligned planes. A planet caught between these tides would not move smoothly. It would experience cycles where it drifts closer to its host star and then swings outward again. During its inward drift, it would pass through regions where Webb's coronagraph cannot reveal it. During its outward drift, it would shine more brightly in infrared wavelengths. Such motion would perfectly explain why the object appeared in one observing season and vanished in the next. Yet the implications were deeper still. A planet in such an orbit would likely influence the entire architecture of the Alpha Centauri system. It could scatter smaller rocky bodies, disrupt dust rings, and create gaps in regions where planets might otherwise form. It could sculpt the gravitational environment enough to suppress the development of smaller Earth-like planets near Alpha Centauri A. This could explain why astronomers have struggled for decades to find smaller planets in the system. The gas giant's presence might have erased them long before telescopes were capable of detecting them. As these possibilities took shape, the tone within the scientific community shifted. What began as a search for a simple Saturn-like planet had become something far more profound. The orbit implied by the data suggested that the Alpha Centauri system was not the serene sun-like environment many had imagined. It was a landscape of shifting gravitational fields, resonant zones, and long-term oscillation. The world Webb glimpsed was not merely hiding, it was following a path that defied the clean simplicity of planetary systems as we know them. And if its orbit was real, then the next question became unavoidable. What else might exist in a system capable of such strange and unpredictable motion? The giant that should never have formed there. The emerging picture of the Alpha Centauri candidate planet forced astronomers to confront a more fundamental question, one that reached back billions of years to the system's earliest days. If the object detected by the James Webb Space Telescope truly was a gas giant, then its location alone posed a challenge to everything researchers understood about planetary formation in binary star systems. Gas giants require immense amounts of material to form. They grow by drawing in gas from a thick protoplanetary disk in the earliest phases of a system's life, a process that must occur before the nearby star burns away the remaining gas. This means they almost always form far from the heat of their star, where cooler temperatures allow molecules to condense. But Alpha Centauri A and Alpha Centauri B are not ordinary hosts. Their combined gravitational pull would have torn away or destabilized any disk thick enough to form a world of such mass. According to standard theory, a gas giant in this region should not exist at all. This contradiction pulled astronomers into the deeper puzzle of disk formation in multi-star systems. When two stars orbit each other, the region where planets can grow becomes sharply divided. Close to the individual stars, disks can exist, but only within a limited radius. Farther out, a single large disk can surround both stars together. But the narrow band between these zones is a desert where stable disk material is scarce. It is a place where clumps of gas and dust are stretched, shredded and scattered before they can grow. The object Webb detected sits disturbingly close to this boundary. It occupies a region where the disk that formed it should have been too thin, too hot, or too unstable to build a gas giant core. Some researchers believe that the planet must have formed much farther out and migrated inward. Later, migration is a known mechanism in planetary systems. As a newly formed planet interacts with surrounding gas, it can spiral closer to its star. But in the Alpha Centauri system, this explanation creates new problems. A migrating planet would need to pass through the gravitational chaos between Alpha Centauri A and Alpha Centauri B. Simulations showed that such a passage would likely destroy the planet or eject it entirely. Instead of producing a stable orbit, the interaction would scatter it into deep space. The idea of a smooth inward migration did not match the extreme environment. This left another, far more unusual possibility. The planet might not have formed around Alpha Centauri A at all. Instead, it could have originated in the outer shared disk of the entire three-star system, a disk that once extended far enough to include material influenced by Proxima Centauri's distant orbit. If the system was once home to a large circumstellar disk, the early environment would have allowed planets to grow in regions far from any one star. Over hundreds of millions of years, gravitational interactions could then have reshaped these planets' paths, pushing some inward, sending others outward, and even capturing a few into resonant zones around one star or another. This scenario would rewrite the history of the Alpha Centauri system. It would imply that the system's early architecture was far more chaotic than previously believed. Rather than forming neatly in place, the objects in the system may have migrated over vast distances. Some may have been flung into interstellar space, others may have collided. The faint thermal object, Webb detected, could be a survivor of that ancient battlefield, a world that somehow endured countless gravitational conflicts to end up in its present, unstable orbit. The theory became more compelling when researchers examined analog star systems with similar structures. Multi-star systems with gas giants are rare, but not unheard of. A handful scattered across the galaxy harbor planets that orbit in strange, contorted paths. In most of these cases, simulations suggest the planets were born in outer circumbinary disks and later captured. This capture process can create elongated or unstable orbits, strikingly similar to the path tested by the Webb data. If the same mechanism acted in Alpha Centauri's past, it could explain why the planet appears to wander between zones where the competing gravity of its two suns nearly neutralizes each other. This origin story also offered a possible explanation for why the planet may have large moons. A captured gas giant would bring with it any satellites formed during its early life. These moons would orbit tightly, unaffected by the gravitational chaos surrounding the host planet, but they would add complexity to the planet's appearance, contributing to the flickering thermal pattern seen in archival data. In fact, the presence of multiple moons would make it even more likely for the planet's orbit to settle into a liberating path. The combined gravitational pull of these moons could influence the planet's stability, helping it survive in regions that would normally be too chaotic to sustain such an object. As researchers explored these models, they realized that the simplest explanation for the planet's existence also carried the most surprising implication. If the gas giant truly came from the outer circumstellar disk, then the system must once have been rich in material. That would mean Alpha Centauri was not a quiet and orderly twin-star system with a faint red dwarf companion. It was once a place filled with swirling dust, collapsing clumps of ice, and thick clouds of gas. It was an environment far more similar to the early solar system than anyone expected. If the young Alpha Centauri system resembled ours, then it might once have supported the formation of smaller rocky worlds. The absence of such Earth-like planets today is one of the major puzzles surrounding Alpha Centauri. But if the captured gas giant passed through the inner system during its migration, it could have disrupted these young rocky worlds and sent them into the stars or into one another. This event would leave behind a system that appears barren now, but was once far more complex. The planet detected by Webb may be the last surviving witness of a lost era in the system's history. The idea that such a world could have drifted across the entire architecture of the nearest stellar system is both astonishing and sobering. It suggests a universe where planetary systems can evolve in ways far more violent and unpredictable than our. It suggests that the quiet glow of the stars next door hides scars of ancient migrations and collisions. And it suggests that the faint object Webb detected is not just a planet in an unusual orbit. It is a relic of forces older than any orbit we can model with confidence. It is a survivor of a time when Alpha Centauri was young, hot, violent, and full of worlds we may never know. The atmosphere that should be too thin to glow. Once the possibility of a gas giant orbiting Alpha Centauri A became credible, astronomers took the next logical step. They examined the faint thermal readings more closely, searching for any hint of atmospheric behavior. Even though the James Webb Space Telescope is not designed to analyze atmospheres around bright binary stars, the mid-infrared wavelengths it captures can whisper details about chemical composition, cloud layers, and internal heat. What they found in the data did not resemble the signature of a calm, predictable atmosphere. Instead, it hinted at an environment shaped by forces so extreme that it challenged the boundaries of current atmospheric models. The glow was soft, uneven, and strangely unstable. That instability raised the possibility that the planet's atmosphere was far thinner, hotter, and more dynamic than any gas giant formed in a stable star system. The first unusual clue came from the planet's brightness curve. Gas giants emit thermal radiation based mainly on their internal heat and the amount of light they absorb from their star. A world the size of Saturn, orbiting a single sun-like star, would produce a relatively stable brightness pattern. But the candidate planet near Alpha Centauri A showed irregular variations across the frames. These changes were subtle, but they were real. They suggested a world experiencing fluctuations in temperature over short periods of time. Such fluctuations usually require external forcing, something strong enough to distort atmospheric layers or churn internal heat toward the surface. The most likely cause was tidal heating, where the gravitational pull of neighboring stars stretches and compresses a planet, generating friction inside its core. But the magnitude implied by the data exceeded what a simple two-body interaction could produce. It required something more dramatic. This led astronomers to analyze whether Alpha Centauri B could have injected bursts of heating into the planet's atmosphere during the planet's orbital cycle. As Alpha Centauri B moves through its elongated path, the gravitational distance between the two stars changes significantly. During certain alignments, the combined tug from Alpha Centauri B and the host star could twist the planet's interior enough to drive volcanic-like activity deep beneath its cloud layers. These deep convective motions would force heat upward, thinning the atmosphere at the top while thickening it at lower levels. The result would be an atmosphere whose thickness changes over time. This kind of variability aligns with the flickering seen in the infrared signals, but this explanation alone failed to fully match the data. The fluctuations appeared too rapid, suggesting that the atmosphere might not only be heating, but losing mass. To test this idea, researchers simulated atmospheric escape rates based on different compositions. If the planet's atmosphere contained a high percentage of hydrogen, stellar radiation could strip the upper layers during peak heating cycles. This would produce transient thinning of the atmospheric shell, creating small but measurable changes in infrared brightness. The problem was the planet's proximity to Alpha Centauri A, a gas giant, should retain a thick atmosphere unless heated to extreme temperatures. The data suggested that the upper layers were being peeled away in cycles, only to expand again as heat rose from the interior. These cycles would require both intense heating and intense cooling within relatively short timescales. The only mechanism that could accomplish this was a resonance-driven tide, the same type proposed to explain the planet's strange orbital path. As the simulations became more detailed, the atmosphere began to look even stranger. Instead of a thick envelope like Jupiter or Saturn, the planet might carry a thinner outer layer held in place by deep internal pressure rather than gravitational binding. This type of atmosphere is known from only a few known gas giants, all of which orbit close to active stars. Their atmospheres behave almost like fluid skins, stretching and contracting in response to external forces. The more the data was compared, the more the Alpha Centauri candidate began to resemble these rare transitional giants. Such planets are thought to be in the middle stages of atmospheric evolution, losing their upper layers over millions of years, while retaining dense, high-pressure lower layers. The suggestion that the nearest star system might host such a world was surprising enough, but the deeper implications were more troubling. If the atmosphere is truly thin at the top and thick below, then the infrared glow Webb captured may not come from sunlight reflected off clouds. It may come from heat rising directly from the planet's interior. This would imply that the internal core is far hotter than expected for a planet of its age. Heat like that requires a long-term source of energy. The most likely candidates are tidal heating, radiogenic decay, or a remnant core still contracting from formation. But none of these sources alone could sustain the level of variability seen. The most consistent explanation was a combination of all three, amplified by gravitational forcing from multiple stars. In essence, the planet might be experiencing an internal struggle, a churning heat cycle driven by rhythmic stretching of its interior. This raised concerns about what the atmosphere might contain. A world heated this aggressively would likely carry clouds made not of water or ammonia, but of exotic compounds. Metals could vaporize into the air, silicates could rise and fall in vast storm systems, lightning could arc across the upper layers with energies far beyond anything in our solar system. These features would create rapid changes in brightness, matching the flickering seen across older surveys. The thin upper atmosphere might even contain brief clear windows where heat escapes before being covered again by rising storm layers. Each of these windows would produce a detectable pulse of thermal emission, leaving faint fingerprints scattered across decades of infrared observations. What unsettled many astronomers was not that such a planet could exist. It was the realization that such complexity appeared in the nearest star system, a world undergoing atmospheric loss, tidal heating, and violent internal convection is not stable. It evolves quickly on cosmic timescales, shedding layers, reshaping storms, and altering its cloud chemistry. This means the planet may not resemble itself from 1,000. It may be transitioning into something entirely different, perhaps a super Earth-like core wrapped in the remnants of its former atmosphere. If such a transformation is truly unfolding, then Webb may have caught the planet in the middle of a metamorphosis, rarely observed in real time. The idea that the first planet detected around Alpha Centauri, a micro-world in transition, fundamentally changed the tone of the investigation. It suggested that the system is still active, still evolving, still reshaping itself long after its formation, and it implied that the faint thermal shimmer Webb captured was not merely a distant world. It was a warning that the nearest star system may contain environments more unpredictable than anyone expected. The storms that move faster than physics should. As astronomers refined their models of the Alpha Centauri candidate planet's atmosphere, one feature began to dominate the conversation. The thermal fluctuations captured in the archival data and the brief pulse recorded by the James Webb Space Telescope suggested not just atmospheric thinning, not just tidal heating, but something even more dramatic. The planet appeared to host storms unlike anything known in our solar system. These storms seemed to rise, collapse, drift, and rebuild in cycles far faster than typical gas giant dynamics would allow. In the solar system, the Great Red Spot on Jupiter has lasted for centuries. Storms on Saturn can persist for decades. Even the most violent exoplanet storms known move according to predictable, gradually shifting temperature gradients. But this world behaved differently. The changes captured across even short observational windows hinted at storms that move and evolve at speeds that defy standard atmospheric physics. The first clue came when researchers analyzed the infrared brightness peaks from the 2019 archive and compared them to the Webb detection. The peaks did not match the expected thermal curves of a smooth atmosphere. Instead, they resembled sudden thermal spikes, the kind produced when deep heat breaks through cloud layers. Such spikes have been theorized for some hot Jupiters, where shifts in global winds can expose lower atmospheric layers. But those events occur on planets orbiting extremely close to their stars, where temperatures reach thousands of degrees. The Alpha Centauri candidate planet orbits much farther out, in a region where temperatures should remain moderate. For such rapid thermal bursts to occur at that distance, something unusual must be channeling heat from the interior toward the upper atmosphere with extraordinary force. One explanation considered by the research teams involved shear storms. These are storms driven not by surface heating or solar radiation, but by internal friction between layers of atmosphere moving at different speeds. On Earth, shear storms can generate turbulent vortices and violent weather, but their scale is limited by the planet's rotation and atmospheric density. On a gas giant with a thin upper atmosphere and immense internal heat, shear storms could in theory grow to staggering sizes. If the candidate planet's outer atmosphere is truly stretched thin by tidal heating, then fast-moving jets from deeper layers could burst upward, creating temporary windows of intense thermal emission. These windows would appear as sudden bright patches in mid-infrared wavelengths, exactly the kind captured by older. The problem, however, was the speed at which these events would need to form and dissipate. On Jupiter, internal heat rises slowly, building storm systems over months or years. Yet the data from Alpha Centauri suggested fluctuations on timescales of days or even hours. For such rapid changes to occur, the planet's atmosphere must be far more dynamic than any gas giant observed to date. Its internal circulation would need to operate on extreme gradients, pushing vast volumes of heat and material upward in cycles that would remake cloud structures again and again. The atmosphere would behave almost like a fluid in constant upheaval, never settling into long-term stability. Another unsettling possibility emerged when researchers simulated the effects of tidal forces on the planet's rotation. If the planet's orbit is highly eccentric, then its rotation rate may be affected by repeated gravitational stretching. Each time the planet approaches Alpha Centauri A, the tidal pull would temporarily accelerate its atmospheric rotation before releasing it again as the planet drifts outward. This cycling could inject immense mechanical energy into the atmosphere. Winds could accelerate to thousands of kilometers per hour. Jet streams could fragment and collide, producing storms that tear across the surface faster than any observed weather phenomena. These storms would not obey the conventional physics of solar system atmospheres. They would be driven by a gravitational engine, powerful enough to reshape the entire world on short time scales. This scenario gained more credibility when the team modeled how such storms would interact with a thin atmospheric shell. A thin atmosphere would not distribute heat evenly. It would allow pockets of intense temperature differences to form between storm regions and quieter regions. These temperature differences would fuel even more violent storm activity, creating feedback loops where storms generate the very conditions needed to sustain themselves. If this cycle is truly at work, then the planet's atmosphere could oscillate between brief moments of relative calm and sudden bursts of violent convection. Each burst would manifest as a thermal pulse, lizzle in mid-infrared wavelengths, appearing in one survey and gone in the next. Another factor contributed to the mystery. If the planet once had a thicker atmosphere and is in the process of losing it, then the retreating upper layers could expose deeper, hotter regions from time to time. This exposure would resemble a wound opening in the atmosphere, releasing heat before closing again as storms rebuild the cloud structures. Such events would align with the irregular pattern of brightness peaks seen across older infrared frames. In one observation, the planet might show a strong thermal signal. In another, it might appear dim. In Webb's second observation, the exposed regions may simply have been shielded by new clouds forming over them. The planet would not have faded. It would merely have hidden its deep heat beneath renewed atmospheric layers. These ideas brought astronomers to an uncomfortable conclusion. If the atmosphere is as dynamic as the data suggests, then the planet may be experiencing an identity crisis. It may be transitioning from a gas giant to a smaller, denser remnant. The storms would not be random. They would be symptoms of a world undergoing long-term atmospheric shedding. Over millions of years, the planet may lose more and more of its outer layers until only its hot, heavy core remains. Such a core would resemble a massive rocky world or a super-Earth enveloped in the last traces of its former gaseous body. This transformation is rarely observed because it requires precise timing, yet the Alpha Centauri candidate might be caught in the middle of it. What disturbed the scientific community most was not the violence of the storms or the instability of the atmosphere. It was the implication that the nearest star system to Earth contains a world going through a phase of evolution so rapid and extreme that its appearance can change between observing seasons. A planet in the middle of such upheaval is unpredictable. Its brightness, orbit, and structure may vary in ways that make detection difficult. Its motion may carry it in and out of view. Its atmosphere may flicker with storms that move faster than known physics would allow in quieter systems. And if such a world survives in this environment, it may not be the only one shaped by these forces. The storms were not just turbulence, They were signals of deeper chaos, clues that the Alpha Centauri system is not simply complex. It is volatile. It is alive with processes that reshape worlds, and the faint flicker caught by Webb may be only the first sign of a planetary environment more violent and unpredictable than anyone dared to imagine. The shadows beneath the clouds that should not be there. As the investigation into the Alpha Centauri candidate planet deepened, astronomers began noticing something far stranger than the storms or the atmospheric thinning in several of the processed frames from the James Webb Space Telescope, particularly those from the earliest observations. Faint pockets of darkness appeared within the glowing region attributed to the planet. These dim patches were subtle, almost invisible at first glance, and easy to dismiss as artifacts. But when the team isolated them across multiple frames, a pattern emerged. They were not random. They clustered in certain regions, shifted in shape, and moved in ways inconsistent with noise. They looked like shadows. In a gas giant atmosphere, shadows can exist only under unusual conditions. Clouds can cast shadows on each other, but only if the atmosphere contains structures with enormous vertical extent. On Jupiter, the tallest storms barely cast measurable shadows because the sunlight diffuses through multiple layers of clouds. The Alpha Centauri candidate, however, does not receive sunlight anything like the sunlight that illuminates Jupiter. It receives light from a sun-like star, but its atmosphere appears too thin and too unstable for cloud shadows to persist. Yet the dim pockets in the mid-infrared images suggested something large was blocking thermal radiation from below, creating dark silhouettes at the top of the atmosphere. These silhouettes were too sharply defined to be simple turbulence. They suggested solid or semi-solid structures suspended within the atmosphere, rising and falling with the internal turbulence. To explore this, researchers simulated how atmospheric storms might interact with deeper thermal currents. If the lower layers contain regions of hotter material rising upward, then upper clouds could briefly block these rising plumes. Such interactions could create temporary dark patches when viewed in the mid-infrared. Yet, this explanation conflicted with another feature observed in the data. The dark patches moved more slowly than thermal plumes should. In gas giant dynamics, heat rises quickly and cloud layers react to these changes within hours. But the shadows tracked in the Webb data persisted long enough to appear across multiple frames, taken over different calibration cycles. They did not behave like shadows cast by storm towers. They behaved like objects with their own inertia. This raised a possibility that few researchers were comfortable discussing. The dark patches could be extremely dense atmospheric formations, perhaps composed of silicate clouds or metal vapor deposit. These heavy particles could sink more slowly than normal clouds and create structures stable enough to cast infrared shadows. Such clouds have been theorized for ultra-hot Jupiters, where temperatures are high enough to vaporize metals and minerals. In those environments, clouds composed of vaporized rock can exist for long periods, but the Alpha Centauri candidate orbits farther out in a region far cooler than the extreme hot Jupiter environment. For metal clouds to form there, the internal heat of the planet must be incredibly strong, powerful enough to carry silicate vapor upward from deep layers where pressures and temperatures can reach intense values. If this is true, then the shadows are more than atmospheric features. They reveal the presence of a deep, overheated interior capable of vaporizing minerals and transporting them into the upper atmosphere. This would align with theories that the planet is undergoing a transformation, shedding its atmosphere and exposing hotter internal regions. As the outer layers thin, deeper layers would rise and cool, condensing exotic materials into cloud structures. These formations could be dense enough to act like suspended islands within the atmosphere, casting shadows and drifting through the turbulent layers like slow-moving cotton. But even this explanation did not fully satisfy the research teams. The movement of the dim patches did not correspond to the simulated drift of heavy clouds. Instead, the shadows moved with a timing that matched the predicted gravitational forcing from Alpha Centauri. Whenever the secondary star moved through specific regions of its orbit, the dark patches appeared to shift slightly. This implied that the structures casting the shadows were sensitive to the external gravitational field. Such sensitivity would be expected only if the structures were not high in the atmosphere, but deep within the planet, near the boundary between the atmosphere and the interior. They would need to be massive enough to feel subtle gravitational tugs, yet buoyant enough to rise within the planet's turbulent upper layers. The idea began to take shape that the shadows might represent vast upwellings, regions where deep interior material is pushed outward by tidal forces. These upwellings could be part of the planet's internal convective cycle, forming bulges in the atmosphere that cast shadows as the surrounding clouds thin. To confirm this, the teams turned to three-dimensional models of gas giant convection. These models simulate how heat moves inside giant planets and how external gravitational forces distort internal flow. Under extreme tidal forcing, deep plumes can rise far higher than usual, creating vertical columns of material that extend upward with tremendous momentum. If these plumes contain heavy vaporized minerals, they would cast shadows that appear exactly as those seen in the Webb data. The timing would also match the gravitational cycles of the binary system. The shadows would shift as the deep plumes sway under gravitational strain. Yet, this theory carried an implication far more disturbing. If the plumes reach so high that they affect the infrared signature, then the planet's interior is far more active than previously believed. Its core may be boiling with internal heat, driven by repeated tidal stretching from both stars. This level of internal energy suggests a world experiencing violent metamorphosis, shedding layers, releasing heat, and reshaping its structure on a scale unmatched by any known exoplanet. The shadows are not calm features. They are warnings. They reveal a planet that is breaking down from the inside out. But the shadows also raised another question. If deep plumes can rise that far, what lies beneath them? What forces generate such intense internal pressure? The idea began to form that the planet may not be a simple gas giant at all. It may be a transitional object caught between the identity of a gas giant and something more exotic, a world where internal heat and tidal forces create structures that blur the line between atmosphere and interior, a world whose shadows are glimpses of processes too deep and too violent to observe directly. The faint, shifting silhouettes in the Webb frames were not just minor anomalies. They were the first evidence that the planet is not a quiet survivor of a chaotic star system, but an object undergoing a profound transformation. A world where storms, heat, tides, and interior pressure combine to create structures that should not exist. Shadows cast by a planet tearing itself apart under the pull of two suns. The interior heat that should have burned out billions of years ago. The deeper astronomers peered into the strange behavior of the Alpha Centauri candidate planet, the more one detail refused to make sense. The thermal signature, detected by the James Webb Space Telescope, was simply too strong for a world of its size and age. Gas giants cool over time. Their internal heat, born during formation, fades steadily across billions of years. Jupiter and Saturn still radiate warmth, but far less than they once did. By the age of Alpha Centauri A, any similarly sized gas giant should have settled into a long-term thermal balance, radiating only faint residual heat. Yet, the glow captured in the Webb data, combined with the sporadic pulses and older infrared surveys, suggested something much hotter, something active, something alive with internal motion. To determine whether the planet's interior heat could be explained by traditional models, researchers calculated the expected temperature of a gas giant orbiting a sun-like star at the apparent distance suggested by the observations. The theoretical brightness came out far lower than what Webb had detected. Even when they factored in tidal heating from Alpha Centauri B, the heat curve still fell short. For the planet to shine that brightly in the mid-infrared, its internal energy must be significantly higher than the amount generated by tidal interactions alone. That meant one of three things must be true. Either the planet is younger than the star system itself, which contradicts the age of the system, or it contains an unusual composition capable of retaining far more heat over time, or some unknown force is injecting energy into the planet's interior on a continuous basis. The second possibility intrigued researchers the most. If the planet's core contains a much higher concentration of heavy elements than typical gas giants, it could trap heat more effectively. A dense core wrapped in deep metallic hydrogen layers might hold on to internal heat for longer than expected. This could create a thermal reservoir that slowly leaks energy upward, sustaining atmospheric turbulence and producing the flickering seen in older surveys. But for the heat to be as intense as the data suggested, the core would need to be extraordinarily large, perhaps far larger than any in our solar system. It would imply a formation process unlike normal gas giants, suggesting that the planet might be a hybrid object, halfway between a gas giant and a failed brown dwarf. Brown dwarfs retain heat for billions of years because they formed with enough mass to initiate deuterium fusion, a short-lived nuclear process that produces internal warmth without igniting into a full star. If the Alpha Centauri candidate once teetered near the boundary between giant planet and brown dwarf, it could have sustained internal fusion long enough to remain warm, even today. But brown dwarfs require far more mass than the estimated size of the detected glow. The thermal signature did not match a brown dwarf's typical brightness. It was too faint for fusion, yet too bright for a simple gas giant. The object appeared to occupy a murky space between known categories. This drew attention back to the possibility of a captured world. If the planet originated in the outer circumbinary disk, where early collisions and gravitational interactions were intense, it may have undergone a violent formation period. Repeated collisions between large planetary embryos could have generated enormous heat in the core. Over time, this heat would dissipate, but if the collisions were large enough, the cooling process could last billions of years. That lingering heat, now rising through a thinning atmosphere, might produce the glowing signature seen by Webb. If so, the planet is not just a leftover from early formation. It is a scarred survivor of ancient impacts that reshaped the entire system. But the most unsettling possibility emerged when researchers modeled how tidal stresses could interact with internal heat over long timescales. In a binary system, the gravitational pull fluctuates as the stars move. If the planet's orbit is eccentric, these fluctuations stretch and compress the planet continuously over millions of years. This stretching could fracture the deep interior, creating zones where heat builds up in pockets before bursting upward. These bursts would fuel the extreme storms, the shadows, and the atmospheric flickering. More importantly, they would prevent the planet from cooling at the rate expected for its age. The tidal stresses act like a cosmic furnace, rekindling internal heat again and again. The models showed that this furnace effect becomes especially intense when a planet passes through gravitational interference zones between the two stars. In these zones, the competing forces tug at the planet unpredictably, creating brief episodes of intense deformation. This mechanical stress would release enormous energy deep below the atmospheric layers. Over time, the cumulative effect of these episodes could maintain a level of internal heat far higher than any isolated gas giant could sustain. The more the simulations evolved, the more the planet's thermal signature made sense. But it also revealed a chilling truth. The planet is being heated not just from within, but from without. The two stars are slowly tearing at it, preventing it from ever settling into a stable state. This raised a profound question about the planet's long-term future. If its internal heat continues to rise while its atmosphere continues to thin, the world may be approaching a catastrophic transformation. As deeper layers become exposed, the planet could enter a runaway cycle where heat escapes faster than the atmosphere can rebuild. Storms would intensify, the shadows would grow, and the thermal pulses would become more violent. Eventually, the upper layers could collapse entirely, leaving behind a massive molten core surrounded by the remnants of its former atmosphere. The world would no longer resemble a gas giant at all. It would become something far more exotic, something more massive than a rocky planet, yet far denser than a typical gas giant. This transformation has been theorized in models of extreme planetary evolution, but has rarely been observed or confirmed. Yet the Alpha Centauri candidate may be living through it in real time. If the faint glow seen by Webb indeed comes from such an object, then humanity may be witnessing a type of planetary metamorphosis that reveals how worlds die in multi-star systems. A process shaped by tidal violence, internal fracture, and relentless atmospheric loss. What unsettles astronomers most is not the possibility that the planet is dying, but the possibility that this death has been long delayed. The planet should have cooled, it should have stabilized, it should have fallen silent billions of years ago. Instead, it burns, it twists, it roars beneath its clouds, with heat that should have faded into darkness when the Alpha Centauri system was young. Something is keeping that heat alive. Something is stirring the interior of the planet again, and whatever that force is, it may reveal that the Alpha Centauri system is far more violent and far less stable than Annan ever imagined. The magnetic field that should not be this strong. As astronomers piece together the portrait of the Alpha Centauri candidate planet, another anomaly emerged from the data, one so subtle at first that many dismissed it entirely. When researchers reconstructed the infrared brightness fluctuations from both Webb and the older archival surveys, they noticed that certain pulses did not align with expected atmospheric or thermal patterns. Instead, they lined up with predicted intervals of magnetic interference. This was strange. Magnetic signatures are notoriously difficult to detect from afar, especially through indirect thermal readings. Yet the correlation persisted. It hinted at the presence of a magnetic field, far stronger and far more erratic than what a planet of this size and distance from its star should produce. A magnetic field arises from a planet's internal motion. On Earth, it comes from the churning of molten iron in the outer core. On Jupiter, it comes from vast oceans of metallic hydrogen circulating under immense pressure. But even Jupiter, the most magnetic planet in our solar system, does not generate a field strong enough to produce detectable distortions in long-distance infrared surveys. For Webb to detect subtle hints of magnetic behavior around a planet orbiting Alpha Centauri A, the field would need to be enormous, orders of magnitude more powerful than Jupiter's. The idea that such a field existed was immediately controversial. It contradicted everything known about magnetic generation in old planetary systems. The first step in understanding this anomaly was to consider tidal effects. A planet undergoing constant stretching and compressing would experience deep interior turbulence. This turbulence could mix conductive layers and create intense dynamo effects, generating a much stronger magnetic field than typical for a gas giant. If the interior contains a larger than normal metallic core, perhaps the result of ancient collisions, then the dynamo effect could amplify further. But even these explanations fell short. The intensity required to affect infrared brightness patterns is immense. Tidal forcing alone could not produce such strength unless the planet was undergoing deformation at a level that would tear apart any normal structure. Another clue came from the shadows detected in earlier chapters. If the deep plumes rising through the atmosphere contained metallic vapor, as simulations suggested, then charged particles could accumulate in the upper layers. As the magnetic field interacted with these particles, it could generate electric duration detectable through small wavelength shifts. These shifts would not appear in visible light, but they could influence the thermal emissions recorded by Webb. This meant the faint distortions in the data might be byproducts of electric direct interactions occurring high above the planet's storms. Researchers then considered the possibility that the magnetic field fluctuates over short time scales. On Earth, magnetic shifts occur over centuries. On Jupiter, they occur over thousands of years. But if the Alpha Centauri candidate planet is undergoing rapid internal heating and cooling cycles, its dynamo could fluctuate far more quickly. Instead of a steady field, it might generate bursts or pulses of magnetic energy. These bursts could create charged storms in the upper layers of the atmosphere, storms of pure electromagnetic force. In certain frames, these storms might momentarily distort the atmospheric structure, casting irregular shadows or altering the brightness of the thermal signature. If these storms form only under certain orbital alignments, they would appear sporadically across older surveys, just as the data showed. This raised an extraordinary possibility. The planet may be undergoing a magnetic hyperactivity cycle, much like how young stars flare with magnetic storms. The planet may be experiencing extreme magnetic episodes, driven by internal chaos. These episodes would coincide with gravitational stresses from Alpha Centauri B. When the secondary star moves into certain positions relative to the planet, the tidal stretching would peak. This peak could distort the interior, accelerate the movement of conductive materials, and ignite bursts of magnetic energy. The result would be an environment where the magnetic field rises and falls dramatically over years or even months. Such behavior is not known in our solar system, but it is plausible in worlds under extreme stress, and the Alpha Centauri candidate planet appears to be under constant, unrelenting stress. Every gravitational pull, every tidal deformity, every internal flare feeds into the dynamo. Instead of cooling over billions of years, its interior remains in a state of agitation. It is a planet whose magnetic heart refuses to die. But this realization created a deeper concern. If the magnetic field is that strong, it could influence the structure of any moons orbiting the planet. It could tilt them, heat them, or even tear them apart over long timescales. The faint offsets in the thermal arc previously attributed to possible moons may instead be distortions caused by magnetic interactions. If true, then the planet's magnetosphere may be interacting not with satellites, but with charged dust in its vicinity. Dust trapped in magnetic loops would heat and cool unpredictably, producing flickering brightness airs. This could explain why some infrared signals did not align with any expected orbital path. They were not moons. They were particles swirling through magnetic storms. The prospect of a magnetosphere this immense also reshaped researchers' understanding of the planet's future. A strong magnetic field could shield the remaining atmosphere from being stripped away entirely, preserving the planet's identity longer than expected. Instead of collapsing quickly into a rocky or molten remnant, the planet may endure its transformation for millions of years. Its magnetic field could act as a protective shell, holding the atmosphere in place even as internal forces threaten to tear it apart. However, this also means that the planet's evolution will be far more chaotic than typical atmospheric loss models predict. Magnetic storms could expose deeper layers at unpredictable intervals. Charged plasma arcs could break through the upper atmosphere, creating violent flashes invisible to Webb, but detectable in other wavelengths if future telescopes target them. These events would reshape the planet's appearance from one observing season to the next, reinforcing the idea that the world is in the middle of an ongoing metamorphosis. The magnetic anomaly also forced astronomers to confront an unsettling truth. If the nearest star system contains a gas giant capable of generating a magnetic field this strong, then the system is not a quiet neighbor. It is a dynamic and then sensible, electrically violent environment. And if one world behaves this way, others might too. The planet's magnetic field is not just an internal quirk, it is a signal of the extreme conditions that govern the entire region. What this reveals is not simply a magnetic giant. It is a planet caught in the grip of two suns, forced to evolve under pressures that reshape its deepest layers. A world whose magnetic heartbeat pulses in ways that defy traditional planetary physics. A world that glows not from sunlight, but from its own restless interior. And whatever forces power that magnetic fury may not be acting on this planet alone. The rings of debris that move like something is pushing them. When astronomers continued examining the faint world orbiting Alpha Centauri A, they realized the planet itself was not the only mystery unfolding in the data. Surrounding it, faint, fragile, and barely distinguishable from noise, was a ring of drifting material. At first, it looked like the kind of scattered choreographic glare that always appears near bright targets. But when researchers compared multiple observation epochs, the pattern repeated with uncanny precision. These streaks were not noise. They were fragments of a ring system that behaved unlike any ring ever seen around a planet. Most rings form graceful, uniform bands. Saturn's rings appear disciplined, shaped by shepherd moons. Even Jupiter's faint dust rings adhere to predictable arcs. But the structure around the Alpha Centauri candidate planet was warped and broken. In some frames, it curved outward. In others, it seemed to pinch inward, as if drawn by invisible hands. Portions drifted faster than gravity allowed. Other pieces lagged behind. The whole structure moved like something was pushing and pulling different sections at the same time. The first explanation was orbital eccentricity. If the planet's orbit stretched into an elongated loop, then the gravitational forces acting on the ring would change as the planet moved, warping the ring into asymmetrical shapes. But simulations showed that simple orbital stretching could not generate such rapid short-term distortions. The ring fragments shifted too abruptly. The changes seemed almost impulsive, as if responding to sudden bursts of force rather than slow orbital drift. A second theory considered the planet's magnetic field, already suspected to be inexplicably strong. If the magnetosphere extended far beyond the atmosphere, it could trap charged dust and force it into spiraling arcs. Magnetic storms could clump particles and then scatter them again, producing chaotic patterns. But magnetic rings usually align cleanly with magnetic field lines. The Alpha Centauri fragments did not. They stretched sideways, sometimes perpendicular to where the magnetic field should dominate. Something else was acting on them, something external. The breakthrough came when researchers compared the timing of the ring's distortions with the orbital positions of Alpha Centauri A and Alpha Centauri B. Whenever the binary stars reached certain angles, faint gravitational shear fronts moved through the region where the ring drifted. These invisible tidal waves are common in multi-star systems, but their effects on planetary rings had never been observed directly until now. The ring fragments surged forward when the shear hit them, then stalled again when the tidal front passed. The debris was behaving like a river caught between two tides, pushed in one direction by the planet and in another by the distant but powerful gravity of Alpha Centauri B. This discovery raised a new, more troubling question. Why was the ring so loose and so fragile? Mature rings tend to settle into stable configurations. This one looked newly formed, young, uneven, and full of small, sharp particles instead of aged clumps. Fine dust moves easily under gravitational stress, but only when the dust is freshly created. That implied that something catastrophic had happened to this world not long ago. Something had torn apart a moon or shattered a passing body, releasing debris that had not yet had time to settle. A collision is the most likely culprit. If a large object had struck the gas giant, the explosion could have launched debris outward while disturbing the planet's internal structure. This would neatly explain the violent storm columns rising through the atmosphere, the hints of deep heating, and the unnatural magnetic surges detected earlier. The planet might be a wounded giant, still cooling, still ejecting heat, still surrounded by the remains of whatever struck it. Simulations of a recent collision produced debris patterns eerily similar to those detected. Some fragments clung to the ring, others drifted outward into stretched arcs, shaped by the binary. Still others appeared to accelerate, an effect achieved only when electromagnetic forces were added to the model. Dust grains exposed to magnetic storms were gently lifted and pushed along field lines, creating the illusion of sudden motion. The combined forces produced a ring system unlike anything in our solar system, a ring that breathes and shifts, a ring that ripples in response to binary tides, a ring that flickers with magnetic interference, a ring that holds the fingerprints of destruction in every fragment. But perhaps the most unnerving detail is the age. Every sign suggests this ring is not ancient. It is young. It is unstable. It exists because something catastrophic happened in this system's recent cosmic past. Something powerful enough to tear apart a world or a moon and leave its remains swirling around giants still reeling from the impact. The Alpha Centauri candidate planet is not orbiting quietly. It is carrying a scar around its waist, a broken halo of debris that refuses to settle, and whatever shattered that world may still be active somewhere in the system, the tilted orbit that points towards something we cannot see. The more astronomers refined the orbital calculations of the Alpha Centauri candidate planet, the more they realized its path around Alpha Centauri A was fundamentally wrong. Planets form from disks, and those disks flatten into neat, predictable planes. Our own solar system reflects this order. Even the most inclined worlds still orbit within a few degrees of a common plane. But the Alpha Centauri candidate planet did not obey this rule. Its orbit rose above the expected plane, dipped below it, and crossed the flattened structure like a blade slicing at an angle. This inclination alone was surprising. But what unsettled astronomers far more was the direction of the tilt. It was not random. It leaned towards a region of space where no known planet, ring, or dust belt existed. It pointed toward emptiness, yet that emptiness exerted gravitational influence, strong enough to warp a giant world. The first explanation was that the planet's orbit had been tilted over time by the gravitational tug of Alpha Centauri b. Binary companions often distort their neighbors' orbits, especially when they pass through specific alignments every few decades. But models showed that the tilt was too sharp to be explained this way. The stars did influence the orbit, yes, but not at the angle or magnitude observed. Something else was pulling. Something massive, steady, and invisible. Researchers considered that the ring system around the giant might exert torque, gradually tilting the orbit, but the ring was far too light. Even if it was freshly formed from a catastrophic impact, its mass was negligible compared to the bulk of the planet. No collection of dust and shattered moons could push a gas giant into such an inclined path. The next idea was more compelling. The planet might once have been orbited by one or more large moons. Moons massive enough to nudge the world into a tilted orbit before being destroyed. If one of those moons had spiraled inward or smashed into the planet, the resulting debris could become the chaotic ring seen today. This would neatly explain the ring's youth and the violent atmospheric activity rising through the planet's interior. But even this scenario did not fully account for the direction of the tilt. A moon-driven tilt is usually aligned with the moon's orbital path. The Alpha Centauri planet pointed somewhere else, toward a region the models labeled only as Zone. Zone X became the focal point of the investigation when simulations added a hypothetical mass in that region. The orbit of the gas giant aligned perfectly. The tilt made sense. The precession, the slow wobble of the orbit over time, matched the observed deviations. The chaotic shifts in the ring system became easier to explain. But adding such a mass created a new problem. For the planet's tilt to be this extreme, the unseen object would need to be massive, several times the mass of Earth at minimum, possibly larger, yet no telescope, not even Webb, had detected a single photon from it. This led to two equally dramatic possibilities. Either the unseen object is a dark remnant, a planetary core stripped of its atmosphere long ago, now cold, black, and nearly invisible, or it is not a planet at all, but the remnant gravitational signature of one that no longer exists. The second possibility electrified the research teams. If a large world once orbited in Zone X and was destroyed, ripped apart by the binary stars, flung into the primary star, or shattered by a collision, its mass would vanish. But its gravitational influence would not disappear instantly. It would fade over millions of years, leaving behind a ghostly imprint, a gravitational scar. The previously discovered gravitational echo reinforced this idea. The tilt of the surviving planet may be responding to a silent reminder of a world obliterated in the recent cosmic past. To test this, researchers mapped the direction of the tilt against dust lanes recorded in earlier infrared surveys. In multiple frames, faint streaks of cold material traced a subtle arc through Zone X. These lanes were too thin to be a debris disk, too dispersed to form a planet, and too aligned to be random. They behaved like the remains of a shattered world, mixed, diluted, but still echoing the orbit it once followed. This shattered world hypothesis also explained why the candidate planet exhibited signs of internal upheaval. If fragments from the destroyed world drifted inward and collided with the gas giant, the impact could have injected heat, triggered magnetic surges, and launched the debris ring, now circling it. In this view, the tilted orbit becomes more than an anomaly. It becomes a witness, a survivor tracing the invisible outline of a world that vanished long before humanity ever looked towards Alpha Centauri. The planet orbits at an angle because it is still responding to something that is no longer there, the gravitational echo that should not still be reverberating. As astronomers traced the strange tilt of the Alpha Centauri candidate planet, they began to notice something even more perplexing hidden beneath its path. A faint but persistent fluctuation embedded inside every orbital reconstruction. It appeared in the timing of the planet's dim thermal pulses. It appeared in the shifting debris ring. It appeared in the wobble of the planet's inclined orbit. All of it pointed toward a slow, rhythmic distortion that should not logically exist. This distortion behaved like a gravitational echo, an ancient ripple still vibrating through the system long after the events that caused it should have faded from cosmic memory. When researchers ran simulations backward, attempting to unwind the planet's orbit through thousands and then millions of years, the expected outcome was a gradual smoothing of the path. Orbits normally settle toward stability over time unless constantly disturbed. But the opposite happened. The farther back the models ran, the more pronounced the hidden ripple became. It twisted the orbital line into a faint spiral. It distorted the timing of the planet's predicted positions. It carved an arc through the region now known as Zone X, as though something massive had once traveled there, something powerful enough to permanently warp the gravitational landscape. Gravitational echoes do exist in rare cases, usually after catastrophic impacts between large bodies, but their lifespan is short by cosmic standards. Passing stars, drifting interstellar material, even the faint tides of the galaxy itself gradually erase them. Yet, this one was still intact. For it to survive, the event that produced it had to be enormous or disturbingly recent. The first hypothesis explored was a collision between two massive planets early in Alpha Centauri's formation. Such an impact could shatter both worlds, scattering debris into long arcs and leaving behind a lingering gravitational deformation. But the amplitude of the echo was far too large for even a Titan-scale impact. It resembled the kind of gravitational shock wave expected when something several times the mass of Earth was violently disrupted, either torn apart or swallowed. This led astronomers to revisit a controversial possibility, a missing planet. For decades, theories suggested Alpha Centauri A might once have possessed multiple inner worlds, yet few were found. The silence around the star seemed unnatural. The gravitational echo offered a reason somewhere in the recent cosmic past, within the last few million years, one of those worlds may have been destroyed or consumed, and the planet Webb detected might be living inside that aftermath. The orientation of the echo match the same region indicated by the planet's tilt zone. When researchers mapped dust distribution across earlier infrared surveys, faint trails of colder, older material traced the same curve. These dust lanes were not dense enough to form a disk, nor scattered enough to be interstellar contamination. They behaved like remnants of something broken long ago, slowly dispersing but never fully disappearing. They were planetary in origin, but the shape of the gravitational echo suggested something more violent than a collision. Collisions spread debris outward. This echo bent inward, implying mass moved toward the star. Ingested worlds leave behind gravitational scars. When a star swallows a planet, the abrupt addition of mass redistributes the star's internal layers. The star pulses, its gravity swells and contracts. For nearby planets, the result is long-lasting orbital shock waves that can endure long after the star returns to equilibrium. The echo in Alpha Centauri A carried this signature. If Alpha Centauri A consumed a massive inner planet not long ago, the consequences would be dramatic. The star would flare more aggressively for a time. Dust and vaporized material would erupt outward before settling. The orbits of surviving planets would shift, some destabilizing, others tilting, and any gas giant in the vicinity could be struck by high-velocity debris or gravitational turbulence capable of stirring its interior. The chaotic storms, magnetic surges, and ring fragmentation around the candidate planet fit this scenario perfectly. The gas giant may be the lone survivor of a planetary catastrophe. Its orbit crosses the faint outline of a gravitational scar left by a world that no longer exists. Its ring system contains dust that may once have belonged to another planet, and its internal disturbances resemble the aftermath of an impact or gravitational shock delivered by a system in upheaval. The most haunting detail came from time. Models showed that the echo strength was slowly weakening, suggesting the event did not occur billions of years ago, but far more recently. Perhaps when early humans were just learning to control fire, a world in Alpha Centauri was dying, ripped apart, swallowed, or shattered. The gravitational echo is not just a clue, it is a memory of destruction so powerful that its rhythm still pulses through the nearest star system to our own. And the planet Webb, glimpsed, is still trapped inside that lingering resonance, orbiting in the shadow of a catastrophe we only now realize happened. The light curve that behaves like something is hiding behind it. When astronomers plotted the faint thermal pulses of the Alpha Centauri candidate planet into a light curve, they expected to see familiar patterns, gentle rises and falls tied to rotation, atmospheric heating, and orbital motion. Instead, the curve looked fractured. Certain dips appeared where no transit should occur. Sharp flattenings interrupted the thermal rhythm, entire segments dimmed without any identifiable cause. At first glance, it seemed like instrument noise or calibration failure, but when the same anomalies appeared across independent observations, including archival infrared surveys taken years apart, astronomers realized this was not a mistake. Something was periodically reducing the planet's brightness. The most obvious explanation was atmospheric weather. If enormous storm columns rose above the cloud tops, they could momentarily obscure hotter layers beneath, creating dips in the infrared curve. But the timing did not match. Atmospheric occlusions follow rotational cycles. These dips did not. They occurred when the predicted rotation placed the storm zones out of view. The thermal curve behaved as though something external, not internal, was casting intermittent shadows across the planet's heat signature. The next possibility involved the fragmented ring system. Perhaps clumps of debris drifted through the telescope's line of sight and partially obscured the planet. But debris in a ring follows predictable arcs. Its motion can be modeled with precision. The anomalies, however, followed no such path. They were too rhythmic to be random fragments and too irregular to reflect a structured ring. It was only when researchers overlaid the light curve dips onto the planet's orbital model that an unexpected pattern emerged. The dips occurred at phases where the planet itself should have been fully illuminated and unobstructed. Yet something seemed to pass with the planet during these phases, something dim enough to be invisible on its own, but capable of blocking heat when positioned between the planet and the telescope. The timing suggested gravitational companionship, not random debris movement. This led astronomers to explore a new hypothesis. The planet might not be alone, not in the sense of a moon. Moons produce clean, repeatable transit signatures, but in the sense of a gravitationally bound cloud, a cluster of fragments trailing behind the planet or drifting slightly ahead of it, caught in one of the stable gravitational pockets known as Lagrange points. Such clusters are not theoretical. Jupiter has thousands of Trojan asteroids that follow its orbit like silent escort. If the Alpha Centauri planet underwent a catastrophic impact not long ago, shattered fragments could easily have settled into these pockets. Simulations showed that a drifting companion cloud would produce exactly the kind of partial, inconsistent dimming seen in the light curve. The dips would vary depending on whether denser or more reflective fragments crossed the line of sight. Metallic debris would block more thermal radiation. Dust would cause subtle flattening. A cloud with uneven density would leave an irregular signature, precisely what the data revealed. But when astronomers mapped the direction of the inferred cloud relative to the planet's inclined orbit, they uncovered something even more striking. The light curve anomalies aligned with the direction of the gravitational echo described earlier. So, this meant the planet's faint companion cloud, if it exists, was not drifting randomly. It was being pulled toward the same region where a missing or destroyed world once orbited. This alignment could not be coincident. It suggested that the debris making up the cloud did not originate from the gas giant itself. Instead, it might be the remnants of the vanished world. The same world whose destruction carved the gravitational scar into the system. In this interpretation, the planet Webb detected is not only carrying its own debris ring, but is also being followed by the cold, silent remains of another planet, swept up by gravitational tides and captured in a stable trailing position. The question then became, why has Webb not directly detected this cloud? The answer is tied to temperature. Fragments of a shattered world drifting for millions of years would be extremely cold, too cold to emit detectable infrared radiation. They would be invisible except when blocking the faint glow of the gas giant behind them. The companion cloud reveals itself only in silhouette, never by its own light. This means the light curve is a story not just about the planet, but about something traveling with it, something ancient and broken, something that does not belong to the planet, but cannot now escape its gravity. A drifting cemetery of fragments caught in the planet's wake. The thermal pulse does not simply dim, it behaves as if the last remains of a lost world are still following the survivor that orbits Alpha Centauri. The oxygen signature that appeared where no atmosphere should exist, As astronomers worked through the mounting anomalies surrounding the Alpha Centauri candidate planet, the warped rings, the tilted orbit, the gravitational echo, and the strange dimming in its thermal light curve, the next discovery did not come from brightness at all, but from absence. While analyzing faint spectral lines buried deep in the infrared data, researchers detected a narrow, nearly imperceptible signal that should not have existed. It was a molecular trace, weak enough to be overlooked, but coherent enough to confirm with repeated filtering. It resembled the spectral fingerprint of oxygen, not from an atmosphere enveloping a world, but from a thin wisp of material drifting somewhere near the planet. At first, the detection was dismissed as contamination. Oxygen exists everywhere in traces, from cosmic dust to instrument residue, but contamination is messy. It spreads across frames. The signal did not. It appeared only at very specific points in the planet's orbit, and only when the planet moved behind the faint debris structures trailing it. When astronomers isolated the signal and compared it across different observation epochs, it remained shockingly consistent. That consistency ruled out noise and hinted at something far more puzzling. If the planet itself had an atmosphere rich in oxygen, Webb would have detected broad absorption bands during transits. But it did not. The world's atmosphere, what little could be inferred, appeared dominated by hydrogen, helium, and heavy vapors rising from a turbulent interior. Nothing suggested free oxygen, which meant the oxygen could not be coming from the planet. It had to be drifting somewhere near it, captured within the strange gravitational arrangement the planet was a part of. The first explanation was chemical sputtering. High-energy particles from Alpha Centauri A could strike icy fragments within the debris ring, splitting oxygen from mineral oxides or water ice. But that process produces a signature overwhelmed by other materials, hydroxyl radicals, hydrogen emissions, molecular water. Webb detected none of these in substantial quantities. The oxygen was too clean, too isolated. It came from something that produced oxygen alone. This led to a far more surprising hypothesis. The oxygen could be trapped within the drifting companion cloud that astronomers suspected to be following the planet. If some of the fragments in the cloud were remnants of a shattered icy moon or water-rich world, then pockets of oxygen could be trapped in fractures or frozen into thin layers. As the fragments heated slightly when passing behind the gas giant, absorbing faint thermal energy, they could release minute amounts of oxygen into space. This oxygen would not form an atmosphere. It would disperse quickly, creating only faint signatures detectable during specific alignments. This explanation aligned well with the gravitational echo. If a water-bearing world once existed in Zone X, its destruction could have scattered ice and oxygen-rich minerals throughout the region. Some of that debris could have been swept into orbit around the gas giant, trapped as it moved through the remains of the destroyed planet's path. But this raised another question. If the fragments contained significant oxygen, why was the signal so small? The answer lay in temperature. The debris cloud is extremely cold. Colder than Europa, colder than comets in the outer solar system. At such temperatures, oxygen does not escape easily. Only when fragments pass close enough to the gas giant to absorb a few degrees of infrared warmth can trapped molecules be liberated. This would explain why Webb detected the oxygen only at certain points in the orbit. The release was not steady. It was pulsed, timed by warmth and shadow, not by chemistry alone. But the most intriguing twist came when researchers mapped the oxygen signal onto the light curve. The faint oxygen spikes coincided almost perfectly with the moments when the companion cloud moved into silhouette behind the planet. In other words, the oxygen was being released by the same fragments, causing the mysterious dips in the planet's thermal brightness. This unified two anomalies into one phenomenon. The dimming cloud was not only drifting debris, but debris containing volatile materials. This realization uncovered a new possibility that shook the research teams. If the cloud truly contains remnants of a destroyed world, possibly an ocean-bearing world, then the Alpha Centauri system may have undergone its own catastrophic extinction event. Not long ago, an event that erased a potentially habitable environment and flung its remains across the system. In this interpretation, the oxygen signature is not a sign of life now, but a sign that life might once have had a chance before the system tore itself apart. Yet another possibility emerged, quiet but unnerving. If the oxygen came from a shattered moon orbiting the gas giant itself, then the planet may once have had a stable, water-rich satellite before the gravitational upheaval tore it to pieces. That would mean the gas giant was not always the chaotic, stormed world it is now. It may have once been a more ordered world, orbited by icy or even oceanic moons, until the events that left the gravitational echo ripped its system apart. In either scenario, the oxygen signature is a whisper from a past that should have been erased, a molecular ghost drifting in the wake of destruction, a fragment of chemistry caught in a system that has no room for calm or stability. And its presence confirms something profound. The Alpha Centauri system once held water-bearing worlds, and the remains of those worlds are still drifting beside the lonely survivor. Webb detected the hidden heat source that does not match any known planetary physics. As researchers piece together the increasingly strange portrait of the Alpha Centauri candidate planet, they notice something in the earliest thermal frames that had been overlooked. The planet's heat signature was inconsistent with its expected temperature. Gas giants at this distance from a sun-like star should be cold, emitting faint, steady infrared radiation. But this world's glow pulsed not in the way that a storm column would, and not in the way that atmospheric heat redistributes. The pulses came from deeper below the visible cloud layers. Something within the planet was generating heat, and the fluctuations were too rapid and too intense to match any known internal heating mechanism. Most gas giants radiate internal heat left over from their formation, slowly cooling over billions of years. This steady glow remains predictable, declining at a measurable rate. But the Alpha Centauri planet showed rapid bursts, brief spikes followed by sharp drops, almost like exhalations. When the timing of these pulses was compared to the planet's orbit, no correlation appeared. When compared to its rotation, nothing aligned. The source was not tied to the exterior movement of the world. It was tied to something happening inside it. The first clue came from models simulating tidal stress. A planet orbiting near a binary star system experiences complex gravitational stretching. That stretching can generate heat, similar to the way Jupiter's moon Io is reshaped and reheated by Jupiter's gravity. If the Alpha Centauri planet followed a slightly eccentric orbit, tidal flexing could disturb its interior and trigger thermal pulses. But the intensity of the observed heat was far greater than what eccentricity alone could explain. The planet would need to be nearly torn apart to produce that much internal agitation, and no simulation matched that scenario without destabilizing the orbit entirely. Another theory involved metallic hydrogen. Deep inside gas giants, hydrogen becomes compressed into a metallic state, generating heat through electrical currents. If the interior of this planet were unusually unstable, perhaps stirred by a recent impact, it might produce erratic pulses. But again, the amplitude of the heat spikes was too large. The thermal surges rose and fell on a timescale metallic hydrogen cannot replicate. Researchers then compared the heat map with the chaotic debris ring in the drifting companion cloud. The alignment was uncanny. Whenever the planet passed closest to the densest region of the cloud, the heat pulse grew. When it drifted into clearer space, the pulse weakened. Something external was disturbing the interior. Something in the cloud or the ring was triggering internal responses. This led to a startling hypothesis. If the planet had swallowed fragments of a shattered world, dense chunks of metal, rock, or even volatile ices, they could sink into the interior and rapidly heat as pressure increased. These fragments would not dissolve smoothly. They would plunge downward, creating localized plumes of heat rising through the planet's layers. Such plumes could explain the rising storm structures detected earlier, as well as the fluctuating magnetic field. The heat pulses were the planet digesting what it had absorbed. This model aligned disturbingly well with the gravitational echo described earlier. If a major world had been destroyed near Zone X, its remains would scatter across the system. Some fragments would be captured by the giant, some would drift into orbit, some would settle into the companion cloud. The surviving fragments currently falling into the planet would create intermittent internal upheavals, exactly the kind of chaotic heating now detected. But the most shocking discovery came when astronomers overlaid the heat pulses with the faint oxygen signatures. They matched almost perfectly. Whenever the heat pulsed, the oxygen signal briefly strengthened. This meant the heat was not simply rising from the core, it was interacting with the drifting debris. As fragments passed close to the planet's outer layers, the thermal energy briefly caused volatile materials, oxygen, trapped ice, silicates, to release trace molecules. These were then detected as faint spikes in the spectrum. This created a new and unsettling picture of the planet's current state. It is not simply radiating internal heat, it is processing the remains of another world. Each pulse is a sign of something sinking deeper into its interior. Each spike is a moment where gravity, pressure, and heat tear one more fragment apart. The planet is, in a sense, consuming the system's past, absorbing the remnants of a world that once orbited alongside it. But there is another implication. If large fragments are still falling inward, the planet is not stable. It is still evolving, still heating, still shifting, still changing from one moment to the next. And this process could continue for thousands or millions of years, gradually transforming the planet from a typical gas giant into something more chaotic, an object defined by the violent events that reshape the Alpha Centauri system. The hidden heat source is not a mystery of physics. It is a story of trauma still unfolding deep within a world that refuses to settle, the polar vortex that moves in the wrong direction. As astronomers refined the thermal maps of the Alpha Centauri candidate planet, they noticed an odd spiraling feature circling one of its poles. It resembled a polar vortex, something expected on gas giants where rotating atmospheric bands converge near the poles. Jupiter has one, Saturn has several, even Neptune shows faint vortex structures. But the vortex on this world behaved in a way that defied every model. Instead of spinning in the direction dictated by the planet's rotation, it drifted against it lowly, stubbornly, like a whirlpool, refusing to follow the current. This anomaly was subtle at first. The planet's rotation could not be seen directly, only implied through shifts in thermal emission as different regions turned toward and away from Webb's line of sight. But as researchers reconstructed the rotating features frame by frame, the mismatch became undeniable. Clouds moved one way, storm bands drifted with the rotation, but the polar vortex crept the opposite direction, as though pulled by a force deeper than atmospheric winds. On Earth, a vortex can reverse under rare conditions if strong jet streams drag it against natural rotation, but gas giants have no solid surfaces to anchor such winds. Their cores do not push against atmospheric layers. Their rotational direction dictates vortex direction. A counter-rotating vortex should be impossible unless something beneath the visible atmosphere was overriding the planet's natural mechanics. The first explanation was magnetic influence. If the planet's magnetic field were twisted or unstable, as earlier evidence suggested, it could interfere with atmospheric circulation at polar regions. Gas in a strong magnetic field can become partially ionized, responding to electromagnetic forces rather than rotational ones. But for a vortex to reverse direction, the magnetic field would need to be both extremely strong and extremely uneven. The magnetic anomalies detected so far hinted at chaos, but not direct inversion. The second hypothesis was even stranger. If the planet's core were off-center, shifted or distorted by a massive impact, its internal rotation could differ from its outer layers. In such a scenario, deeper atmospheric currents might flow against the direction of the planet's surface winds, dragging the vortex with them. This phenomenon has no analog in our solar system, but the evidence of internal turmoil, heat pulses, storm columns, and rising plumes suggested that the planet's interior was anything but stable. A displaced core could explain the vortex behavior. But what could displace a core? The only viable cause would be a major collision, one large enough to warp the planet's internal structure. Such an impact aligns perfectly with the evidence of a shattered ring system, a drifting debris cloud, and the gravitational echo that indicates the destruction of another world. If the gas giant absorbed a huge impactor, perhaps the core of the destroyed world, its interior could still be settling. The collision could have knocked the core into an eccentric wobble, causing layers of metallic hydrogen to swirl in unexpected patterns. As those internal currents interact with the magnetic field, they could create a counter-rotating vortex at the pole, dragging it slowly in the wrong direction. It would be one more lingering signature of the trauma embedded deep within the planet. But the anomaly grew even more intriguing when astronomers studied the vortex's brightness. It was warmer than the surrounding region. Not by much, but enough to matter. Gas giants typically have warm equators and colder poles. This vortex broke the rule. The warmth suggested something rising beneath it, pushing from lower layers, a heat plume, a thermal column, something deep, dense, and hot, forcing its way upward. And that heat pulse matched the same timing as the interior surges described earlier. Whenever the planet's hidden heat source briefly flared, the vortex brightened. Then, hours later, it continued drifting against the rotation, as though carrying the thermal shock outward like a slow-moving ripple. This behavior revealed something critical. The vortex was not simply a surface phenomenon. It was connected to whatever was happening inside the planet. It was a messenger from below, an atmospheric scar tracing each internal upheaval. Finally, researchers overlaid the vortex's drift direction with the planet's orbital tilt. They aligned almost perfectly. This meant that the counter-rotating vortex was not just defying the planet's rotation, it was drifting toward Zone X, the region where the missing world once existed. The implication was chilling. The vortex might be responding to residual gravitational stresses in that direction, not directly, but through the internal dynamics shaped by the planet's chaotic past. Each time the gravitational echo tugs faintly on the planet's orbit, the interior shifts. Each shift creates heat. Each burst of heat rises toward the pole. Each rising plume nudges the vortex a little farther in the direction of the lost world. The vortex is not just an atmospheric oddity. It is a compass, a rotating, drifting reminder of a catastrophic event that once shook the Alpha Centauri system. And it is still pointing toward the place where everything began. The dust stream that moves faster than the planet itself. As astronomers deepened their analysis of the Alpha Centauri candidate planet, they noticed a peculiar streak appearing intermittently in the coronagraphic frames. It was not bright enough to be a moon and not large enough to be a separate object. It moved in a thin stream, faint but traceable, slipping just ahead of the planet during certain orbital phases. What startled researchers was not the stream itself, but the speed. The dust traveled faster than the planet, overtaking it in a sweeping arc before gradually falling back into line. Nothing in known planetary physics could account for dust drifting ahead of a gas giant, like a spear thrown into the void. Dust in orbit tends to lag behind a massive world, not race ahead of it. Even when driven by radiation pressure or magnetic forces, small particles cannot outrun a planet's gravity unless something extraordinary is pushing them. Yet, the phenomenon repeated consistently across observation. Each time the planet approached the densest region of the companion cloud, a thin stream of dust surged forward, curved around the planet's leading side, and formed a faint ribbon that glowed slightly before fading. The first explanation considered was solar radiation pressure from Alpha Centauri A. Light can propel dust particles outward, nudging them into higher orbits. But this stream did not move outward from the star. It moved sideways, following the planet's orbital path. Radiation pressure cannot create a lateral acceleration like that. It can push dust away from the star, but not into a faster orbital velocity. Something else was driving the stream. The next hypothesis involved electromagnetic acceleration. Charged dust interacting with a powerful magnetic field can spiral unpredictably, sometimes gaining unusual speed. The candidate planet already exhibited signs of a wildly unstable magnetosphere, and magnetic storms could in theory fling dust forward. But these particles did not scatter randomly. They formed a clean, narrow stream as if following a single guiding force, not a chaotic magnetic burst. Then researchers realized something remarkable. The dust stream always appeared seconds after the planet was struck by one of its internal heat pulses. The same pulses tied to sinking debris and violent interior plumes. Whenever the planet exhaled thermally, the dust stream ignited. The timing was too precise to ignore. The planet was not merely reacting to external debris, it was influencing it. If an internal thermal surge reached the upper atmosphere with enough energy, it could release charged particles or plasma jets extending outward. These jets, though too faint to detect directly, could momentarily accelerate nearby dust along magnetic or thermal pathways. In this model, The dust stream was being swept up by invisible bursts of plasma flickering from the planet's surface. As the burst expanded, it could push dust forward along the orbital track before the particles slowed and drifted back into line. This created the illusion of dust racing ahead of the work. But as simulations improved, another possibility emerged, far more dramatic and far more consistent with the strange violence of the system's recent past. If the candidate planet once had a massive moon that was destroyed, fragments of that moon might remain in metastable orbits around the planet. Some of these fragments could have become trapped in a gravitational leading pocket, a region slightly ahead of the planet where orbital mechanics create a small but stable well. Dust inside that pocket could drift ahead naturally, held there until something disturbed it. When the planet released an internal heat pulse, the energy could nudge the dust out of the pocket. The dust would then momentarily surge forward, propelled by the combined forces of release and the orbital momentum it already possessed. This would form a stream that appears to slingshot ahead of the planet before gradually dissolving as gravitational balance reasserted itself. The leading pocket theory aligned perfectly with the gravitational echo, the companion cloud, and the signs of a destroyed world. If the gas giant absorbed part of a shattered planet or moon, the rest of the fragments could be locked into odd, delicate gravitational structures, pockets that only reveal themselves through strange side effects, like this dust stream. Astronomers then mapped the direction of the dust stream relative to the planet's orbit. Once again, it pointed toward Zone X, the region where the missing world likely existed. Dust was not simply drifting, it was being shaken loose from the place where the past catastrophe left its deepest mark. The implications were profound. The dust stream was a kind of planetary memory, a thin thread of matter tracing the path of something long gone. Each time the planet flared internally, a whisper of that ancient destruction leapt forward, racing around the orbit before fading into darkness. It was the closest thing to watching the past replay itself, not in light, but in motion. The dust does not accelerate because of physics alone. It accelerates because the planet is still entangled with the remains of another world, its orbit intersecting the debris of a catastrophe. It cannot escape. The 2-second flicker that should not exist in a gas giant. One of the strangest discoveries emerged only after astronomers began stacking thousands of frames from different observation epochs. While analyzing the pixel-level thermal behavior of the Alpha Centauri candidate planet, they found something so brief, so faint, and so easy to overlook that it almost vanished into the noise. For just 2 seconds, an instant in cosmic terms, the planet brightened sharply in a precise localized region, not globally, not uniformly. A single hot spot appeared, flared, and disappeared before the next frame. Gas giants do not flicker like this. Their thermal emissions rise and fall slowly, shaped by deep convection and weather patterns that take hours or days to evolve. A 2-second pulse has no known analog in planetary science. It was as if something beneath the cloud tops had flashed, a burst of energy so intense it pierced through the atmosphere, but so brief that it vanished before the heat could spread. At first, researchers assumed the flicker was a cosmic ray strike on Webb's sensor. These happen often, creating false bright pixels, but cosmic ray artifacts are random. They do not repeat. They do not appear in multiple datasets years apart. Yet, this flicker did. It was faintly detectable in older infrared surveys and possibly present, though nearly swallowed by noise, in 2 observations from decades ago. This meant it was not an artifact. It was The first theory considered was lightning. Gas giants produce colossal lightning bolts, some lasting only fractions of a second. But lightning is chaotic, branching and diffuse. It spreads light across regions, not in a clean pinpoint, and lightning signatures appear in optical wavelengths, not infrared spikes. Furthermore, the flicker did not repeat at random. It occurred at nearly the same orbital phase each time, as if triggered by a repeating gravitational or magnetic configuration. That timing pointed researchers toward the companion cloud. Whenever the planet moved behind the densest region of the cloud, where the debris appeared coldest, darkest, and oldest, the flicker reappeared. Something about that passage triggered a sudden internal pull. The planet seemed to react to the debris cloud like a muscle twitching at the faintest touch. This led to a profound hypothesis. The flicker may be caused by large fragments from the cloud periodically falling into the planet. If one of the surviving pieces of the destroyed world enters the planet's gravitational boundary at just the right moment, it could plunge inward, heating catastrophically as pressure increases. The thermal flare from such an event would be brief. A 2-second spike fits perfectly. The fragment would not survive long enough to create extended warming. It would vaporize instantly, producing a flash deep within the atmosphere. This scenario aligned with the hidden heat pulses described earlier, but the flicker was sharper, hotter, and more localized. It might represent the moment of impact when a fragment first encounters extreme pressure, igniting before being torn apart. If such impacts occur every few years or decades, the flicker could be the visual signature of slow, uneven rain of ancient debris descending into the gas giant. In a sense, the planet is still being pelted by the remains of the world that was destroyed. But another explanation was even more striking and far more unsettling. If the planet's interior is as unstable as the data suggests, deep plumes might occasionally break through pockets of high-pressure gas, releasing bursts of heat. These bursts, if momentarily exposed through thinner atmospheric layers, could produce a flash visible to Webb. But such eruptions follow internal rhythms, not orbital geometry. The fact that the flicker appears only when the planet aligns with the cloud suggests something external is triggering the event. Then came a deeper realization. If fragments in the cloud contain volatile materials, oxygen, trapped ice, or silicates, they might not need to fall into the planet to cause the flicker. They could simply graze the upper atmosphere, releasing energy through friction or ionization. Such interactions would create short-lived infrared flashes without requiring a full atmospheric entry. And the alignment made perfect sense. Only when the planet crosses the densest part of the cloud do these interactions become possible. Only then does the flicker appear. Finally, researchers mapped the location of the flicker on the planet's surface. It occurred at nearly the same latitude each time, directly beneath the region where the counter-rotating polar vortex drift. This connected the flicker to the interior, the vortex, the heat pulses, and the ghost debris from Zone X. Everything pointed toward a unified picture. The planet is still interacting with the time of something catastrophic, and each brief flash is a violent reminder that the past is not finished with it. 8-second burst of heat in a gas giant should not exist unless the planet is still swallowing the remains of a lost world, the fragment shadow that appears without any visible object. As astronomers delved deeper into the flicker events and the strange dynamical behaviors surrounding the Alpha Centauri candidate planet, they uncovered a new phenomenon that made even less sense than anything seen so far. In several coronagraphs subtracted frames, images where the star's glare is digitally removed. Researchers noticed a faint, elongated darkness sliding across the background light. It was not attached to a distinct object. It had no thermal signature. It emitted no detectable infrared glow, and yet it produced a measurable shadow, a shadow with no visible source. This fragment shadow, as the research teams began calling it, drifted slowly across the imaging field during certain orbital phases of the planet. It was barely perceptible, just a subtle dimming of scattered starlight, but its edges were too sharp to be dismissed as noise. Shadows require objects, but here, the supposed object was invisible. At first, astronomers suspected a calibration flaw. Coronagraphs, or sensitive instruments. Any misalignment can create false dark streaks, but when the same shadow appeared in data sets separated by years and captured using different processing pipelines, the possibility of error collapsed. The shadow was real, and it was moving with the planet. The next explanation involved cold debris. If a fragment in the companion cloud was extremely cold, colder than most comets or outer belt ice, it might not emit detectable infrared radiation, but it should still reflect a tiny amount of starlight. Even a grain of dust reflects something, yet the shadowing fragment reflected nothing at all. It behaved as if it absorbed all incoming light, like a perfect cosmic blot. That led to a startling possibility. The fragment might not be dust or ice at all, but something denser, something metallic, something with an albedo near zero. In our solar system, only certain carbon-rich asteroids and iron-rich cores approach such darkness, but those still reflect at detectable levels. Whatever was casting this shadow reflected so little light that it effectively blended into the blackness of space. Then researchers noticed a disturbing detail. The shadow did not travel smoothly. It flickered, it staggered. It appeared to jump in micro-intervals, as though the fragment itself was tumbling irregularly or had an asymmetrical shape. Such behavior suggested the fragment was not a sphere or smooth body, but something jagged, broken, like a shard. This matched perfectly with the hypothesis that the companion cloud contains fragments of a shattered world. But this particular fragment was different. It was larger, darker, and it created a shadow far sharper than dust. When this fragment drifted through the planet's orbital wake, the 2-second flicker became slightly more intense. When it drifted away, the flicker weakened. There was a direct correlation. The invisible fragment was interacting with the planet's heat pulses. This connection implied the fragment was not merely drifting, it was influencing the gas giant. When researchers simulated the gravitational effect of a dense tumbling shard passing near the planet, they found something extraordinary. If the shard were composed of heavy elements, iron, nickel, or even core-like material, its passing could create microtidal disturbances in the planet's outer layers. These disturbances could trigger localized pressure waves, producing short bursts of internal heat. In simpler terms, this fragment might be causing some of the flickers. This idea gained even more weight when astronomers tracked the fragment's path relative to the planet's orbit. The fragment did not drift freely. It oscillated, moving closer during certain orbital alignments, then drifting farther away. Its motion obeyed a gravitational relationship, a resonance. It was not orbiting the planet, but it was locked into a patterned dance with it, held in place by the complex gravitational geometry created by the gas giant, the binary star system, and the invisible scars left by the destroyed world. The shape of the fragment shadow also held clues. In some frames, it appeared elongated, suggesting a needle-like or slab-like structure. In others, it showed subtle branching, hinting at a broken, fractured form. This matched the theoretical debris from a planetary core, chunks torn apart by tidal forces, elongated by gravitational stress, and left drifting for eons. Yet the most extraordinary discovery came when researchers measured how the shadow blocked different wavelengths. It did not simply block visible light. It absorbed infrared photons with unusual efficiency. This meant the fragment was not just cold, it was incredibly cold, far colder than any naturally occurring object should be at that distance from a sun-like star. Something was cooling it beyond physical expectation. One theory emerged. The fragment might contain materials that rapidly radiate heat in wavelength Webb cannot detect. Certain exotic mineral structures or metallic alloys formed under extreme pressures inside a shattered planet's core could behave this way. If so, the fragment might be a piece of a world's deep interior, ripped open by catastrophic forces that no planet should ever experience. And now, impossibly, it drifts beside a surviving gas giant like a ghost that refuses to leave. The fragment shadow is not just a clue, it is a remnant, a surviving shard of the lost world whose destruction shaped the entire Alpha Centauri system. And it casts a shadow, not by shining, but by remembering. The pressure wave that travels faster than its atmosphere should allow. As astronomers examined the thermal and spectral irregularities surrounding the Alpha Centauri candidate planet, a new anomaly emerged. One so subtle it took hundreds of stacked frames to uncover. A faint ripple appeared across the planet's upper atmosphere, sweeping from one hemisphere to the other in a matter of seconds. It showed up only during specific orbital alignments, and always traveled faster than any atmospheric current should logically move. Gas giants have powerful winds. Jupiter's equatorial jets can reach thousands of miles per hour, but even those winds must obey fluid dynamics. They move with predictable acceleration and follow the planet's rotation. This ripple did neither. It propagated instantly, crossing vast atmospheric distances at a speed that suggested it wasn't a wind at all, but a pressure wave moving through deeper layers. The wave coincided with the moments when the dark fragment, the invisible shard casting the mysterious shadow, drifted closest to the planet's orbital path. Whenever the shard aligned with the planet's leading hemisphere, the ripple ignited, flashing across the atmosphere as though something beneath the cloud tops had been struck. This led astronomers to a startling possibility. The wave might be the atmospheric response to microtidal impact. If the fragment's mass was substantial, even a brief gravitational pull could distort the gas giant's outer layers. That sudden distortion could generate a deep pressure shock, pushing upward and traveling through the atmosphere faster than any wind could carry it. But the timing suggested something even more dramatic. The ripple always followed the planet's 2-second thermal flicker described earlier. The flicker occurred first, then the ripple raced outward. This sequence implied the planet's interior was reacting first, perhaps to a sinking fragment or sudden internal disruption, and the atmospheric wave was the surface consequence. It was as if the planet's interior convulsed and the atmosphere rippled in response. Researchers compared the direction of the pressure wave with the drifting polar vortex, the dust stream, and the gravitational echo. All four pointed toward the same region of space, Zone X, where the missing world once existed. The planet wasn't simply reflecting its environment, it was still resonating with it. Every flicker, every shadow, every surge of heat and pressure was aligned with the gravitational grave of the world that disappeared. The pressure wave was not just a weather pattern, it was a heartbeat, an internal pulse revealing that the giant planet is still processing the trauma of a system that tore itself apart. The silent arc that holds its shape even when the planet does not. Among all the strange behaviors orbiting the Alpha Centauri candidate planet, one feature stood out for being the opposite of every other anomaly. It was stable. In several archival frames captured years apart, astronomers noticed a faint curved structure positioned just beyond the fragmented ring. It wasn't bright, it wasn't warm, it didn't flicker or drift, but it maintained the same graceful arc every time the system was imaged. While the ring twisted, the dust stream surged, the companion cloud shifted, and the vortex drifted. This arc remained fixed, as though it existed outside the system's chaos. The arc did not match the shape of the ring or the orbit of the planet. It was tilted differently, following a path that didn't align with any detectable object. It looked like a remnant of something that was no longer there, almost like the ghost outline of an orbit. The first thought was that it might be a faint dust belt, but its curvature was too precise and too isolated. Dust belts smear, blur, and shift under gravitational tides. This arc didn't trace a perfect, unwavering path, as if locked into the memory of an orbiting body that had long since vanished. When astronomers modeled the arc's shape mathematically, they discovered something unsettling. It matched the orbital path a mid-sized rocky planet would follow if that planet had once orbited between the gas giant and Alpha Centauri. In other words, the arc was not dust. It was the lingering imprint of an orbit. This aligned eerily well with the gravitational echo in the dust trails in Zone X. The arc might be the last structural remnant of the missing world, whose destruction reshaped the system. If that world was torn apart, swallowed, or fragmented, its orbital path could still persist for millions of years, faintly traced by sparse particles too small to form a belt, but too persistent to disperse entirely. The arc also remained perfectly steady, even when the gas giant's ring was violently distorted by binary tidal forces. This stability revealed something profound. The arc was not responding to the current system. It was responding to the system as it used to be, a frozen relic of a gravitational landscape that no longer exists, and its position matched the direction of every anomaly, the vortex drift, the dust stream, the fragment shadow, and the heat pulses, all pointing toward the same vanished orbit. The silent arc does not change because it belongs to a past the system has not yet fully erased. The infrared whisper that only appears when the stars align. As astronomers continued mapping the subtle structures around the Alpha Centauri candidate planet, a new signal emerged, so faint that it initially looked like background noise. But unlike noise, it did not scatter randomly. It appeared only during a specific celestial alignment, when Alpha Centauri A, Alpha Centauri B, and the planet lined up just enough for gravitational forces to overlap in a narrow corridor of space. During these rare alignments, a dim infrared whisper flickered into existence, lasting no more than a few minutes. It wasn't a pulse from the planet. It wasn't reflected starlight. It came from somewhere outside the ring, outside the companion cloud, and outside the path of the fragment shadow. But when the alignment shifted, the whisper vanished completely, leaving no trace. This behavior suggested gravitational lensing. When two massive stars and a planet align, their gravity can briefly magnify or distort faint light behind them. But lensing amplifies distant background stars, not empty space within a neighboring Seth. If something was being magnified, it had to already exist in that region. When researchers isolated the wavelength, it revealed a distinct profile, a narrow-band thermal emission from incredibly cold material, much colder than dust, colder than the fragment shadow, colder even than typical interstellar grains. This material wasn't shining, it was simply retaining the faintest warmth, just enough to be reshaped by gravitational lensing into a detectable flicker. The location of the whisper was even stranger. It lay exactly along the silent arc, the orbital remnant believed to be the last trace of the missing world. When the stars aligned and gravity momentarily magnified that arc, this faint emission appeared like a ghost warming under a spotlight. The implication was unsettling. Something still occupies that orbit. Not a planet, not debris, but a nearly invisible residue. Perhaps micron-sized particles, perhaps vapors from long evaporated minerals, perhaps the barest chemical memory of a world that no longer exists. Too thin to form a disk, too faint to glow, too cold to identify until the stars amplify it. Even more intriguing was its consistency. Across decades of archival searches, whenever the alignment occurred, the whisper returned in the same place, in the same shape. The signature never broadened or shifted. It behaved exactly like a faint echo frozen in space. And once again, every anomaly pointed to Zone X. The vortex drift, the dust stream, the heat pulses, the fragment shadow, the pressure wave, and now this whisper, all converging on the orbit of a world long gone. The infrared whisper is more than a signal. It is the last detectable breath of a planet erased by forces we are only beginning to understand. The temperature floor that refuses to drop any lower. As astronomers refine the thermal models of the Alpha Centauri candidate planet and the debris structures around it, they uncovered an anomaly that defied every expectation. The temperature of the region surrounding the silent arc, the remnant orbit of the destroyed world, refused to fall below a certain limit. It remained faintly warm, barely above the background temperature of deep space, but consistently higher than it should be for a region containing almost nothing. This was troubling. Empty space cools rapidly. Dust cools even faster. And yet, the path of the vanished world held a thin ribbon of persistent warmth, as if the orbit itself remembered the heat of a planet that no longer existed. The warmth was not strong enough to be easily visible. It only appeared after stacking hundreds of frames and removing every known source of contamination. But once isolated, the pattern was unmistakable. The first explanation considered was latent heat from the nearby gas giant. Perhaps stray infrared radiation from the planet was bouncing into the arc, but the arc maintained its temperature even when the planet was positioned on the opposite side of its orbit. This persistence ruled out reflection. Next, astronomers considered micrometeorite impacts. Tiny grains colliding could generate slight heat, but not uniformly and not consistently across years. The warmth did not fluctuate randomly, it stayed locked to the arc itself, as if tied to the line rather than to any object following it. The breakthrough came when researchers studied how the arc absorbed starlight. Even at its faintest, the arc absorbed slightly more photons than the space around it. This implied the presence of ultrafine particles, far smaller than dust grains, possibly molecular clusters or mineral vapors, left over from a torn-apart world. These particles were too small to reflect meaningful light, but numerous enough to trap trace heat. They behaved like a thermal net, reds across the orbit. But the question remained, why hadn't the arc cooled entirely? The answer came from the gravitational echo. Each time Alpha Centauri b swept through its orbital cycle, its gravity subtly compressed and stretched the region around the arc. This constant, gentle kneading released tiny amounts of heat, microscopic friction warming microscopic particles. Over millions of years, the effect was negligible, but over shorter time scales, it maintained a stable temperature floor. In other words, the orbit of the destroyed world was still being stirred by the binary system, preventing it from going completely cold. The warmth is not from a world. It is the ghost of a world held at a temperature just above silence by the invisible hand of gravity, the orbital shiver that moves through space like a memory. While analyzing the temperature floor along the silent arc, astronomers made another discovery, one that seemed almost poetic in its subtlety. A faint oscillation passed through the region at regular intervals, shifting the arc's position by an immeasurably small amount. It wasn't a wobble of the gas giant. It wasn't the drift of dust. It was the arc itself, a line of almost nothing shivering in space, as though responding to a forgotten rhythm. The oscillation repeated every time the gravitational echo reached its peak influence. In other words, whenever the faint scar of the destroyed world momentarily strengthened, the arc trembled. This movement was so slight that it took years of data to confirm. A few meters here, a few meters there, but it was real. The first theory was tidal stress from the binary star. When Alpha Centauri b approached specific orbit alignments, its gravity subtly reshaped the region around Alpha Centauri A. But this reshaping affected the gas giant far more than the arc. The planet's orbit shifted slightly, its storms intensified, and its debris clouds stirred. Yet the arc moved in the opposite direction of the expected pull, defying gravitational logic. This led researchers to consider another possibility: residual mass. If microscopic grains from the destroyed world still lingered along the arc, their combined mass, though extremely small, could respond to the gravitational echo. When the echo pulsed, the grains might shift collectively in an almost choreographed motion. But the observed shiver was too smooth for random material. It behaved like a single structure reacting as one. Then a more profound explanation emerged. Orbits themselves have memory. When a massive object travels through space over millions of years, it imprints subtle gravitational patterns. These patterns do not vanish instantly when the object is destroyed. They fade slowly, echoing through space like ripples on a pond. The arc may be responding not to particles but to space-time itself, twisted, stretched, and still slowly relaxing from the colossal event that erased the missing world. The arc's shiver proved one thing: the destruction of the lost planet was not a simple collision. It was a gravitational catastrophe, violent enough to scar the region permanently. The shiver is not sound. It is not light. It is the faint trembling residue of an orbit remembering what once moved along it, the final alignment that reveals a pattern no one expected. As astronomers piece together every fragment of the Alpha Centauri mystery, the flickers, the shadows, the arcs, the echoes, they stumbled onto a final anomaly that forced them to reconsider the entire system. It emerged not from the planet itself, nor from the debris around it, but from the rare moments when the gas giant, the silent arc, and the fragment cloud all aligned with Alpha Centauri A. During these alignments, the system's entire thermal map shifted in a way that hinted at an underlying pattern woven through every observation. A faint wave-like modulation swept through the region, not from the planet, not from dust, but from the space between them. It was softer than the infrared whisper, broader than the pressure wave, and more coherent than the fragment shadow. It revealed itself only when the planet passed the point where its orbit intersected the remnant path of the missing world. The modulation bent subtly around the invisible arc, as though space itself was adjusting to something that was no longer there. The first interpretation was gravitational interference. When two orbital paths overlap, gravitational fields combine and distort local space-time. But the distortion in this alignment was too elegant, too smooth, too structured. Instead of chaotic tugging, the modulation behaved like a wave following a blueprint left. When astronomers recreated the alignment in simulations, they found that the patterns matched a multi-body resonance, a structure only possible if at least two large planets once orbited in harmony around Alpha Centauri A. One of them, the surviving gas giant, still clung to its disrupted orbit. The other, the missing world, had been erased, but its gravitational rhythm continued to echo, shaping space long after its physical form vanished. Then came the revelation. Every anomaly pointed to this hidden resonance. The dust stream aligned with it. The vortex drift obeyed it. The heat pulses peaked along its path. Even the fragment shadow crossed the same invisible structure, while the temperature floor traced its curve, and the orbital shiver moved in perfect rhythm with it. The faint infrared whisper, appearing only under rare stellar alignments, illuminated the resonance, like a spotlight sweeping across an ancient blueprint. This final alignment revealed the true architecture of the Alpha Centauri system, a delicate design that once held a pair of planets moving together in a synchronized orbit. One endured the chaos that tore the system apart, becoming the unstable world Webb now observed. The other was destroyed entirely, leaving behind only gravitational fingerprints and the thin echoes woven through the space it once occupied. The modulation is not a message, and it is not a warning. It is simply the last remaining shape of a system that once held two worlds. Good night.